These lectures, they tend to be at the end of the entire crash course, and I can't really focus too much on them because we already spent a lot of time. We end up being late. Everyone's already dead, so it's difficult to sort of, get them to understand everything. But right now we have a lot of time. We have 4 hours, and the truth is we'll probably only need 3 hours to finish these 2 lectures. So let's get started as soon as I figure out how to share screen. Just 1 second. All right, before we start, does anyone have any questions about yesterday? If we happen to have time, at the end, we can do a quick little 10-minute summary over everything, just to help you sort of recap what we did yesterday and to recap what we're doing today. But all right. So you have probability distributions first, right?
Yes.
Okay, perfect. Let's share screen. All right. Yeah, I'll see if I can do a summary of everything. We'll see how it happens. Let's just try and focus on these. So the truth is, this lecture, there are 2 concepts, and that's it. The next lecture pretty much repeats the same concept that we're discussing here. And just 1 second. And in the second, so just if you understand those 2 concepts really, really well, there are just a few more, definitions, things that we add on to sort of complete the picture. And, the main bulk of everything is just with these 2 concepts, okay? So the first one is called binomial distribution, and the second one is called multinomial distribution. He really wants you to know how to calculate whatever things he asks whenever he tells you, in this binomial distribution, what's the probability of this, this, this? In this multinomial distribution, what's the probability of this, this, this? This is the bulk of what these 2 lectures are about. So we're going to start with probability distributions, all right? And if you have any questions, like we agreed, feel free to stop me. And if you at any time feel like we need to take a break, let's just take a break. It's fine. So with that said, let's just start. Let me get the pen out, and yeah. So this is just a filler slide. So look, basically, when we talk, the reason we talked about probability so much is because now we're actually going to deal with probability distribution. So when we have a distribution, here's what he will ask. He'll tell you, hey, look, in this distribution, which has a mean of 10 and, for example, a standard deviation of 6, what's the chance that you can land on, for example, 12 or even more? So what's the chance of landing somewhere here? So that's why we've been studying probability for so long, because you have to know the basics of probability in order to answer a question like this. And this is an example of answering a multinomial distribution. The only difference with the binomial distribution is that it's not really endless. There are specific fixed cutoffs, and we'll discuss it more. But this is the bulk of the concepts. All you need to know is how to actually figure out what's the chance of getting 12 in this, for example, distribution. What's the chance of getting 4 or even less? So what's the chance of getting all of this? What's the chance of getting it randomly if you pick 1 person out of this entire population? That's what this entire lecture is about. So let's keep going and let's see until we get to it. So he starts off by just giving you a little reminder about what variables are, and where variables can change. They can either be independent, like for example, if you take y equal mx plus b, remember that these 2, are their constants. This is the slope, but x is the independent variable, y is the dependent, because you can change x freely, but then whatever answer you get, it'll become y. So y is not really as free to change. You can technically change it, but indirectly by changing x. So x is the independent variable. Otherwise, you can say it's the predictor, it's the explanatory, it's the exposure, and then the independent is the outcome, the response, whatever happens like that. So it's the same idea that you learned, for example, in high school, of what x is the independent variable and y is the dependent variable, but it's the exact same logic to it. It's just using different names like predictor and response as opposed to x and y. And someone's asking something. Yeah, so we'll talk about Z table. It'll probably be given into your exam, or if what I, when I had the question, we were the first batch to start with online quizzes. They when the question came up, they would put a little file on the question. Then you click on it, and then it gives you the Z table. So you'll probably get the Z table in the exam, and we'll talk about what the Z table is. Just we don't want to jump too far ahead. We're still in the sort of beginning of the lecture where you're still revising some of the basic key concepts. So this is all good. We already know all of this. So it's giving you the types of quantitative variables. We talked about the discrete where you only have integers. You can't have, for example, 1.2. It's not allowed. But continuous, you can have decimal, you can have ratio, so on and so forth. And ordinal, technically, it is a kind of quantitative variable because you're quantifying things. For example, if you rank them like 1, 2, 3, and 4, and 5, you know, you technically are giving numbers. And then he's showing you that you can sometimes put categories onto these variables, like how we said we're transforming data. Like, for example, we're turning it from, like we're turning BMI, we're turning this sort of, we're turning all these numbers, which are technically continuous, into pretty much categories, which are an ordinal. Right? They're ordinal because you're pretty much turning from going from like underweight to having more weight to having more weight to having more weight to having more weight. So clearly there is an order, but the exact magnitude of difference is not that clear. Notice how here this is only 1 point of difference. This is like from 0 to 15. This is only 1 point of difference. This is 2.5 points of difference. So the magnitude of difference between one group to the other isn't the same. So this is an example of turning a quantitative variable into a quantitative variable into a categorical variable. This is all just a revision of what we did earlier in the second lecture about nominal and ordinal and discrete and continuous and data transformation, time to event, so on and so forth. So this is really, so far, nothing we've seen is new. These are just more examples. And here is the BMI example. All right, now we're getting into the actual meat of the lecture. So what are probability distributions? Think of first a distribution. When we say probability distributions, we mean that, hey, if we have this sort of distribution, what's the chance of getting someone that's here or less than all of this? This is what we call probability distributions, that we understand what the curve looks like. So how can we use the information we know about the curve to figure out how likely it is to find someone at a specific point in the curve, or less than that, or more than that, or so on and so forth? There are a lot of steps to it, but the first problem that happens, and I really want to be clear about this from the beginning, the first problem that happens when people are trying to understand this is they just memorize the steps and then they just apply them in the exam. Now, that's all right, but you're going to forget it. And, when it comes time for the final, if you try and revise this, it's going to be a nightmare. And you need to know this stuff for the final lectures anyway. So there's a better way of understanding why we use this formula, why we do it like this, or there's a logic to what you're doing, not just following steps. So if you see yourself following steps over steps over steps, that's fine, but at least know why you're doing this step and why you're doing this step after it, why you're doing this step after it. And we'll talk more about it as we keep going on. So he talks here about empirical. Empirical basically means that, theoretically, if you throw a coin, if you toss a coin, technically the chance of getting heads or tails is half and half. So if you theoretically toss a coin 100 times, it should be 50 heads and 50 tails, right? So 50-50, right? The problem is that with empirical, if you actually do the experiment, it might not be 50-50. It might be, 52 to 48, or for example, it might be 62 to, for example, 40 or 38 rather. So the entire idea is that with empirical, it means you aren't necessarily thinking about just theory. You're actually applying whatever you're doing, and then you're getting certain results. This is what they do. This is how they find the estimates, for example, for how many people have HIV, how tall are people, or in this case, and for example, how many people are dying from COVID-19. They're getting this distribution. That notice how the older you are, you're more likely to die, and they found this association because they found this probability distribution. They found this actual distribution. So this is them collecting data and then plotting it, as opposed to just our theory of, hey, every single piece of information is going to be like this. And that's not true. This is just theory. Just like how we talked about, our coin and how it's supposed to be 50-50, but it's not. So the reason it's not is because we, apply empirical, the empirical sort of law to it, we don't just think of theory. So this is, again, just a filler slide. We're really not getting into the meat of the lecture. It'll come soon. So here's where we're kind of starting. He's starting to tell you that, hey, if we have a variable x and we want to find the probability of finding this variable x, then how do we notate that? We do probability of x, and that's how you properly notate it. You sometimes see me writing probability, or without the parentheses, probability A just straight away. I just do that to shortcut it, but the proper notation is like this. He's just adding the slide to show you it's all right. Now we've officially started with binomial distribution. Okay. Now his example is great, but it goes too fast, too quick, and shows too many concepts way too quickly. So we're gonna stop right here. Okay, we're gonna go to a completely blank screen, and I'm gonna show you what he's trying to say. So let's go back to Zoom. Share screen, and nope. All right, just this. Share screen, and there we go. All right, so here's what we're talking about when we say binomial distribution. I need everyone with me. I don't want to. Basically, I don't want it to create a situation where I don't know where you lost me. So for that reason, just try and, the second you feel like you're lost, just tell me so that we don't have to keep repeating from the beginning. Because this is a long, long problem, and there are a lot of concepts to be shared in this entire problem. So we're gonna start right now. Here's what the problem is. And remember, this entire thing is about binomial distribution. All right, I'm gonna keep that here so that we never forget that this is about binomial distribution. So his question goes like this. If you have a guy and a woman, and they want to have a family, and they had, let's say, 4 children, all right? So they want to have, for example, this is child A, this is child B, this is child C, this is child D. Now, he's a carrier for sickle cell. So that means, he has one good A and a bad A. And she's also a carrier for sickle cell. So she has one good A and one bad A. So the first thing that I want to ask, you guys all took genetics, what's the chance that a child, any child, having the disease, and what's the chance for just one child not having the disease, right? So just think back to your Punnett square. I want you all to do the Punnett square. Oh, the chat's like dying. All right, 1 second. The chat's I haven't, it just told me that Zoom meetings is not responding. All right. So let's go back. Yeah. All right. Forget carrier. So what's the chance of people being affected? Sorry, people being affected, and what's the chance of people not being affected? Carriers are not affected. They're just carriers, right? They're not affected by the disease. So what's the chance of having the disease? Right? It's going to be like this guy's completely normal. This guy's a carrier but not affected. This guy's a carrier but not affected, and this is affected. All right. Yeah. So all of you I like your answers. So 3/4, they're not affected. We can all agree. Forget if they're carriers or not. That's not what the question is asking. 3/4 are not going to be affected. So 3 out of 4 not affected. They don't have the disease. 1/4 will have the disease. Correct? That's from genetics, that you all understand this, and you can all agree that these are the probabilities. And this is the probability of having sickle cell. This is the probability of not having sickle cell for a single child, like a single birth. A single child might have it, might not have it, right? Completely independent from any other birth. So, for example, if this man and this woman were to have a child, that child has a 1 in 4 chance of having a disease, a 3 in 4 chance of not having a disease. And I hope we can all agree on these 2 numbers, right? We all found them fair and square. Now, here's where the question gets interesting. He tells you this couple will have 4 children, all right? And he asks you, what's the chance of none of them having sickle cell? All right, what's the chance of all 4 not having sickle cell? So going back to the probability lecture, this here we're using an intersection since we want them all happening at the same time. We want them all happening at the same time. Now, I don't want you guys to answer because I already saw an answer that's wrong. It's fine. Point is, don't answer for now. What did we learn? What did we learn in the probability lecture? When it's an intersection, what do? We multiply, right? All right. So I want everyone to answer this question right now. What's the probability of the first child being affected? Or not being affected, rather. What's the chance of the first child not being affected? Okay, so the chance of the first child is 0.75. What's the chance of the second child not being affected? 0.75, right? What's the chance of the third child not being affected? 0.75. What's the chance of the fourth not being affected? It's going to also be 0.75. Now, I told you, we want all of them happening at the same time. So the only way that's going to happen is with intersection, not union. We don't want union here. So what do you do with intersection? You multiply, right? When you multiply all of them, there's a very easy way to summarize it. 0.75 to the power of 4. Are we all agreeing on this? Do you all understand? What was the question? The question is, what's the chance of all 4 children, if they were to have 4 children, A, B, C, and D, this couple that's, heterozygous, what's the chance that all 4 do not have the disease? All 4 of the children. Since each person's chance is 0.75, 0.75, 0.75, and 0.75, then you're going to multiply all of them together because it's intersection. Then you're going to have 0.75 to the power of 4. And whatever this is, that's going to be the probability. So you tell that couple, hey, your probability of, I'm just going to find out what the answer is, because just to make it easier. All right, so 0.75 times 0.75 times 0.75. All right, so we got 0.316, and then there's 4, so it's fine. Yeah, 0.316. So we'll just round it to 6. So that's the probability. So you have around a 31% chance, 32% chance that all your children will not be affected. You all agree with me on this, right? This one's easy. This one's easy. But like, why multiply if each child's probability? Yeah. Look, again, someone asked something. Maryam, you need to revise the probability lecture. Why multiply if each child's probability does not affect the probability of the second child? That's the definition of intersection. You always multiply when you want things happening together. When they don't affect each other, that doesn't mean you still don't multiply. When they don't affect each other, we just call them independent events, meaning that this probability will not affect this probability, which makes sense. Look, this probability is 0.75, and this probability didn't change. It's still 0.75. This probability also didn't change. It's 0.75. And remember, this is why I'm telling you from yesterday's lecture, we need to always, you guys always need to ask questions, because if you didn't get it, you're not going to get all this stuff. So did everyone understand why we're multiplying? It's because the question wants all 4 to not have sickle cell at the same time. So for all of them not to have sickle cell at the same time, it's intersection. So for intersection, you have to multiply all of them together. And the chance is going to be 31% pretty much. Yeah, all right, perfect, you got it. Okay, now let's take it up a notch. Next scenario. We have child A, child B, child C, and child D. All right, so this one is a bit more complicated. Again, I don't want you to answer too quickly because this is how you're going to get mistakes. I just want you to answer step by step. So what's the chance that only one child, right? One child has the disease out of all of the 4. All right, so here's what you're supposed to do. So here's what can happen. Let's say the first child got affected. So what are we going to do? We're going to do 0.25 times the other 3 can't be affected. So they have to be 0.75 times 0.75 times 0.75. And you can summarize that into 0.25 times 0.75 to the power of 3, right? That's just the same way. It's just summarizing it, right? So this is the chance, if you do that, you're going to get a certain value, right? But remember, I said that this is only if the first child got affected. What if their second child got affected? What if their third child got affected? What if their fourth child got affected? So remember, when you're talking about, child getting affected or not getting affected, when they're, in the previous example, when they're all not getting affected, there's no different way of, them all not getting affected. It's just one way, all of them not getting affected. But when you talk about only one getting affected, well, it could be the first one, it could be the second one, it could be the third one, it could be the fourth one. So for that reason, what we're doing is we're actually repeating this again and again and again. We're saying, all right, so what if the second one got affected? So the first one's fine, 0.75 times 0.25 times 0.75 times 0.75. And that's the probability of the second child being affected, only the second child being affected, and the rest being normal. Now we do this again for the third child. So 0.75 times 0.75, because that's the second child. And the third child, it's his turn to get affected, 0.25. I'll tell you why the order matters in just a second. Let's continue this. Just memorize the order matters for now. And when I'm done with all of them, I'll explain why the order matters. So, but you all understand that, hey, we have to do this because the first child could be affected, the second child could be affected, the third child could be affected, the fourth child could be affected. So let's do this again. 0.75 times 0.75, then the third child's okay, 0.75 times 0.25. Now, in case, I'm gonna, tell you the truth here, whatever value you get here, it's basically going to be, let's say, X. This entire thing is X. Would anyone argue with me telling me that this thing right under here, this is not X? No, it's also X, because when you multiply four numbers, let's say you multiply 2 times 4 times 4 times 4, or if you do 4 times 2 times 4 times 4, these will always be the same answer. These will always, always, always be the same answer. So can we all agree that this value, whatever this value will be, it'll be a certain number that will be completely equal to this value, which will be equal to this value, which will be equal to this value? All right, you're all getting it. So since they're all the same value, what we can do is actually just add them all together, because this is the probability of the first one getting affected. This is the probability of the second one getting affected. This is the probability of the fourth one getting affected. This is the probability of the third one and the fourth one getting affected. So the entire idea is that this represents, when you add all these probabilities together, this represents the entire probability of one child and only one child getting affected, because it could have been the first, could have been the second, could have been the third, could have been the fourth. All right. Now let's talk about why the order matters. Let's say you told them that, all right, let's actually find out what this equals. I want to find out what one of these equals. 0.25 times 0.75 times 0.75 times 0.75. All right, so the answer is 10%. 10%, which is like 0.10, right? All right. Now, let's say you don't want to do all of these things. The order doesn't matter. You only want to do this one thing and then tell them your chance is 10%. This would be wrong. Now, the reason it would be wrong is because this is only if the first child got affected. This is, for example, they had their first child, he got affected, and then the other three did not get affected. Well, what if, they got their first child, but he was okay? Does that mean that, khalas, they're not going to get a child that's affected? Because you only gave them the percentage if the first child is affected. That's the only percentage you gave them. You said, okay, if it's the first child that got affected, but the rest are okay, then that means that it's 10%. But you need to give them the other percentages. You need to give them the percentage of the second child getting affected, which is this one, the third child getting affected, which is this one, and the fourth child getting affected, this one. Add them all together, and that's the that's the chance of one child getting affected, either the first, second, third, or fourth. You get it? So when you're doing each single one, we're multiplying because we want them. For example, we want one affected and the other's normal. We want one affected and the other's normal. One affected and the other's normal. One affected and the other's normal. Notice I'm saying and. So since I'm saying and, all of these are multiplication when you consider them together. But the reason I add them later is because this is the probability of the first being affected, or the second being affected, or the third being affected, or the fourth being affected, assuming that once one person is affected, the others will be normal. You got it? So this is why I'm adding these probabilities, right? You can't just say that, oh, hey, the order doesn't matter, and just give them 10%. So did it make sense? This part is incredibly important. So knowing that the first child is affected, what will be the probability others are affected? Can you repeat this part? I'll repeat this part. Look, your question, Samiha, I'll get to it. It's incredibly complicated because knowing the first child is affected, what's the rest of the other will be affected? It's basically all four being affected. So I know it's confusing. So we're gonna repeat it. Look, the beauty of today is that we have a lot of time. We have a lot of time, and this concept is crucial to understand because it's one of two concepts. So there's no point in me just speed running through it, and then there you go. You need to go and just understand everything else by yourself. No, we're gonna do this over and over and over again because you all need to understand this. Now, okay. We're just gonna tackle one like small thing. Forget all the calculation. I just want the concept of it. I just want to explain to you the concept of it. So we're gonna get a new slide here. All right, we're gonna name. Yeah. Okay. Yeah. So I like the way Bushra mentioned. So just for the people who understand this so far, if the couple asked you, what's the chance of the first child being affected while the rest are normal, you tell them 10%, because this is the chance of the first one being affected while the rest are normal. But if they said, what's the chance of one child getting affected? One child, not the first child, one child. Well, it could be the first one, could be the second one, could be the third one, could be the fourth one. So it's wrong to just give them this probability. It's wrong to give them this probability. I know a lot of you are getting confused. It's fine. Like, this is not an easy concept. It's not like the second someone like understands it, they just, they see it or they understand it. Yeah, you got to like give it a few times. So let's tackle this. I think I know what the concept that you guys are missing is. So to help you understand this, let's do this again, but just for the sake of simplicity, let's name. So the answer would be 40%. Yeah, it would be 40%. I think, like, since it was 10.5%, it will be like 41 or 42%, something like that, because there's decimals after it. Because this is not like this is not 10%, it's like 10.5. So 10.5 times 4 would be like, I don't know, 42. I think 42%. So yeah, it's something like that. Point is, but it's like close to 40%. But yeah, now let's repeat this concept. Let's take a little, step away from just the calculation, and let's understand the idea of, does the order matter? Why are we doing this? All right, so let's name the actual 4 children. So let's name the first one. Or you know what? I think sticking to letters. You know what? Okay. Let's just name them as superheroes. Let's take the first one. The first one is Batman. All right. The first one is Batman. Second one is Superman. Right. Super. Third one is Iron Man. Right. All right. And the fourth one, I have no idea what other superheroes are there. I need someone just to give me another superhero. Spider-Man. Yeah, How could I forget Spider-Man? All right, Spider-Man. All right. So look, what's the chance that Batman has sickle cell, but the others don't have sickle cell? All right. I made it very specific. I only want Batman being affected, but the others, I don't want them being affected. So it's going to be very simple. It's going to be 0.25, but the rest have to be 0.75, 0.75, 0.75. You get it? No. Wait. I'm seeing a lot of you say 0.25. Where the hell did everything go? All right. Listen to the question very carefully. Don't answer yet. Just listen and then answer. What's the chance that Batman is affected, but the rest are not affected? I want them all happening together. So what do you do when it's intersection? What do you do when there's an intersection between, you want all of them happening together? You multiply all of them, right? So what's the chance of Batman being affected, but the other ones, Superman, Iron Man, and Spider-Man, they're not going to be affected? Let me see what everyone's saying. Yeah, so it'll be 0.25 times 0.75 times 0.75 times 0.75, which ultimately ends up being 10% or 10.5. Yeah. So all of you understand this, right? Because I specifically said only Batman, right? Now here is where it becomes tricky. What is the chance? But if we said what is the chance of Batman being affected without mentioning the others, yeah. If I told you what's the chance of Batman being affected, it's very easy. It's just 0.25, right? But I'm saying what's the chance of Batman being affected, and the other superheroes are not affected. Now here's where it becomes tricky. Here's where I did all of these over and over and over again. What's the chance of one superhero being affected and the others are all right? Right? So one has to be affected, but the others are all right. So you just keep repeating this. You keep doing one of these as Batman, then another one as Superman, then another one is Iron Man, then another one is Spider-Man, and then all of those percentages, they'll be the same. They'll be 10, 10, 10, 10. Then you add them. Now, here. I know you all know this. If you have X plus X plus X plus X, how do you simplify this? What do you say? How do you simplify this? X plus X plus X plus X times 4. So it's 4x, right? So if one of these is 10% and that's our X, then it's going to be 4 times 10%. So the ultimate goal of that question is going to be 40%. Did this make sense? Because I'm not saying what's the chance of just the first child being affected and everything else is fine. I'm saying what's the chance of one child being affected? Well, it could be the first, it could be the second, it could be the third, it could be the fourth. So did that make sense? Again, look, the only person that's going to make a question in the exam complicated is yourself. Read the question, get your morning coffee, read the question well, and just answer what the question is asking. Don't overthink it. Don't try and think of it intuitively. Put the formulas in front of you. Try to actually see what he's asking and try and answer it. If he was to ask, what's the chance of Batman being affected and the rest are normal, it will be 10%. What's the chance of one of those superheroes being affected while the others are normal? And it's going to be 10%, one says Batman, plus 10%, one says Superman, 10%, one says Iron Man, 10%, one says Spider-Man. And then you're going to add all of them because it's either the first one getting affected or the second one or the third one or the fourth one. That's why we're adding. All right. So I really hope this concept was like incredibly clear. Okay. That's why back here, I didn't just stop and say the chance of one of the children being affected is, where's my mouse, is 10%. I told them, no, I have to do one as the second child, one as the third child, one as the fourth child, then add them all together. All right. So this is good. I hope a lot of you, what coffee do you recommend today? I drink black coffee. I don't like the cappuccino and everything like that. So I think black coffee is the best, but like, this is just, coffee is a world, man. Like, I don't even know all the different types of coffees. All right. So right now, so what's the probability of Iron Man being affected and all the others? Yeah. So what's the probability of, let's see, Iron Man being affected, but the others are normal? It's 10% because it's going to be 0.75 for Batman, 0.75 for Superman, 0.25 for Iron Man, and 0.75 for Spider-Man. This is the exact same as this, and this was 10%, so this is also going to be 10%. So yeah, right. Now let's kick it up a notch. Now let's go. What's the chance? Right here, to calm your horses. I know everyone wants to jump on this question. What's the chance that two of the superheroes, I'm going to put them all up here. So we have Superman, we have Batman, we have Iron Man, and we have Spider-Man. I'll give them SP. What's the chance of two of them being affected and two of them not being affected? Right? What's the chance of child A or B being affected? All right, Nawaf. I'll answer all of these questions that are like this, but for right now, let's just understand the basic principle. Then we'll answer all of these questions, okay? So what's the chance of two of them being affected? Well, hold on. Let's take the first two. Let's say it was Superman and it was Batman, okay? So it's 0.25 times 0.25, and then Iron Man's not going to be affected in this case, so 0.75, and so is Spider-Man, so 0.75. Now, this is just the first one, all right? So this will be like what? I need someone to calculate it. 0.25 times 0.25 times 0.75 times 0.75. All right, so it's 0.035, right? So it's 0.035. Now here's the kicker. It could be Superman and Iron Man who's affected. So it could be, for example, Superman. All right, let me get rid of the S. I'll just do it straight away. So 0.25 times 0.75, because Batman's okay, times 0.25, because Iron Man's affected, times 0.75, because in this case, two are normal and two are affected, right? In this case, we took Superman and Iron Man. So this will be 0.035. Now, I'm not going to keep doing this. I'm just going to, because it's going to take too long. I'll just do it quickly. So the third one, will be Superman and Spider-Man. So it'll be 0 or 2, 25. Just this 2 is like 0.25. And this will be 0.75 times 0. We said Iron Man's fine, so 0.75, and this will be 0.25, right? So 0.25, 0.75, 0.75, 0.25. And this will be also 0.03, the chat's in the way, 0.035, okay? And now we finished Superman with the others. Now we have Batman. So let's do Batman's thing. Well, we have Batman and Superman. Hold on. We already did this one. Remember we did, here it is. So we're gonna skip that one. There's Batman and Iron Man. So we're gonna do 2, and then, Superman's fine here. 7 times 2 times 2 times 7. And this will also be the same. This will be 0.33. Bushra, I'll show you the easy way. But right now, I'm really focusing on the concept. I don't want you just putting in the formula and then off. So right now we have 1, 2, 3, and 4. What's left? We have Batman and Superman. So it's going to be 7, 2, 7, 2. Then last but not least, we have Iron Man and we have Spider-Man. Now I'm not going to do Iron Man and Batman because we already did that one, right? It's right here. Batman and Iron Man. We don't do that one anymore because we already did it. Last one, we have Iron Man and Superman. So we're going to do, or Spider-Man, sorry. So we're going to do 7, 7, 2, and 2. Now, how many do we have here? We have 1, 2, 3, 4, 5, 6. Well, I wish there was a way we can simplify x plus x plus x plus x plus x plus x. How do you simplify this? You just do 6x. What is x? It is this value. So it's going to be 6 times basically whatever this value is, right? Or you can just do it this, right? You can do just 6 times 0.25 times 0.25 times 0.75 times 0.75. That's another way to find the answer. That's just a very quick way. But see, the reason is because if I just put this straight away, none of you would understand what I'm doing. But now you know where the 6 came from. You know where the 0.25 came from. You know where this came from. You know where this came from. You know where this came from. So don't just plug in numbers. All right, plug in numbers, of course. But like, you need to understand where you're putting the numbers in, right? So the final answer, someone solved this for us, it's 0. There's no way it's 0.844. I'm going to check your work. I'm really sorry. All right, so it's 0.25 times 0.25 times 0.75 times 0.75 times 6. So it's 0.21. So it's 0.21, right? All right, so let's take some questions. We knew it's multiplied by 6 after writing all that down, counted the rows. How can we know it's multiplied by 6? Yeah, so how can we know it's 6? That's important. Now, let's say you don't want to do like me. You're going to waste a lot of time doing all of this to figure out that it's just 6x, right? How can we find out this number very quickly? Well, there's a formula for that. So it's called combination. Maybe you took this in maybe ND, whatever. Maybe you took this in high school. But basically, remember this factorial? So yeah, there's a formula for this. So n minus 1, or no, n minus d was it? Yeah, n minus d, and then factorial. So let's take 6, or not 6, no. Let's take the example we just did. So how can we get 6 here? So how do we use this formula? Basically, d is the number of people that are diseased, all right? D is just like, it's a coincidence that d just happened to be diseased, but like just use it like that. So d is the number of children that will have sickle cell or will have the disease. N is the number of children overall. So what do? We do combination. Maybe the n was up top. I don't really know. Point is, I'm terrible with notation. Let me get a new slide. So it's going to be a combination of 2, because we want 2 children affected, and we have 4. So it's going to be basically, since it's n exclamation mark, this will, let me just do it straight away. So it's n exclamation mark. What is n? It is 4. 4 exclamation mark, 4 factorial. That's how you call it. Then it's going to be d factorial. So it's going to be 2 factorial. Here's our d. It's 2 factorial. And then it's going to be into n minus d. What's n minus d? Well, that's 4 minus 2. It's just 2, and then factorial. Remember, factorial is on the outside in this factorial is on the outside. So first, you remember PEMDAS, the parentheses first, then exponents and whatever, blah, blah, blah. Basically, you first finish the parentheses, then you go on to the factorial. So I did the parentheses first. I did 4 minus 2, then factorial. So now what is factorial? It's basically, if it's factorial 4, then 4 times 3 times 2 times 1. If it's factorial 7, 7 times 6 times 5 times 4 times 3 times 2 times 1. So it's just, a way to signify that you're going to multiply by each number over and over and over again by going less and less and less. So 4 times 3 times 2, 4 times 3 is 12, times 2 is 24. So it's 24 over 2 factorial is 2, because it's 2 times 1. 2 factorial again is just 2. So 2 times 2, that's 4. So it equals 24 divided by 4 equals 6. So look, we got 6. That's how you got the 6 that's right here. You see, you don't need to do all of this that I'm doing, but this is important to explain the concept. But you just need to do this formula, which is combination, and there you go. You're going to get your answer straight away. It's going to be 6. Can we use calculator in the midterm? I think you can. I'm not sure. I wish I was the person to make your exam. But like, I just give you all the calculators. But like, I think you're using the exam solve calculator. So it's still the same. I mean, it just makes the calculations easier. So yeah, just check with everyone. So I don't get the factorial part. All right, so what part don't you get about it? So I'll show you. 4 factorial equal 4 times 3 times 2 times 1. So what is this? I just do it very quickly. I do 4 times 3 is 12, then times 2 times 1. So what is 12 times 2? Times 1 equals 24. Yeah, okay, so you got it. So yeah, just plug in this formula, and there you go. You're gonna get it. So now let's try and do another one, but let's use formulas, and I'll show you how fast you can really do it. All right. So the next question tells you this: if we have Superman, Batman, Iron Man, and Spider-Man, the next question tells you what's the chance that 3 of them are affected. All right, so 3, first thing you do combination. So you say, oh, we want 3 and we want 4. So it's going to be 4 factorial. I'll show you. It's really fast to do it. And then you say 3 factorial into 4 minus 1. So 4 minus 1 is going to be 1. So 1 factorial, you can just cross that out because it's going to be 1. 3 factorial, it'll be 3 times 2. So this will be 6. 4 factorial will be 24. So 24 divided by 6, you'll get 4. I think someone wrote 8. So 6 factorial, 24 over 6, you get 4. Right? So you can all agree with me that there will be 4 combinations, right? Can all of you just say yes or yeah? All right. So I'm seeing I saw some yeses. All right. So then what do we do? Well, what's the chance of 3 of them getting affected? So it's going to be 0.25 times 0.25 times 0.25 times 0.75. These are the 3 affected, and this is the last one. And since I have 4 combinations, I just do times 4. You put this in your calculator, that's your answer. So you get it? So look, it's extremely simple. It's very simple. 4 minus 1 is 3, not 1. Yeah, but remember it's, 4 minus 3, sorry. 4 minus 3 is 1, yeah. 4 minus 3. I just do really, really quickly. So yeah, so I meant 4 minus 3. So why is it 4 minus, 4 minus 3, I'm sorry. It's 4 minus 3. Can you do that one more time, please? All right, so we're gonna do it one more time again. It's fine. So Superman, Batman, Iron Man, Spider-Man. what's the chance that 3 of them are affected? So it could be any 3. It could be the first 3, then, or, you can actually flip it. So what's the chance of only one being normal? So it could be the first one being normal, the second one being normal, the third one being normal, the fourth one being normal. I don't get what numbers to put in the numerator and denominator. Okay, so let's go back to the formula. All right, so look, erase all ink. All right, you have combination. It's 2 things. There's n and there's d, okay? And then n minus d, right? N is the number of things you have overall. So in this case, we have 4 children. So n in this case is 4. D is the number of people that are diseased. So in this case, the one we're doing here where there are 3, we're going to do where it's 3 that are affected. We should put it as 3. Where is it? So we should put it as 3. So this will simplify to the n will be 4. So n equal 4 and d equal 3. So it'll be 4 factorial over 3 factorial into 4 minus 3, which is 1 factorial. Now, 1 factorial is just 1, so get rid of that. You can just simplify it. 4 factorial is going to be 4 times 3. That's 12 times 2. That's 24. So that's 24. Just cross that out to make it simple. And 3 factorial, that's 3 times 2 times 1. 3 times 2 is 6. Times 1, it's still 6. So it's going to be 24 over 6. And 24 over 6 is going to be 4. And that's the number you put next to all the probabilities. And you multiply it by x, X is the probability that I mentioned. Right? So that's how you use combination. So let's repeat this one more time. So what's the chance that 3 of them are affected? What's the chance that all, any 3 are affected? So it's going to be 0.25. I'm just going to do this one first. 0.25 times 0.25 times 0.75. All right, now we need a number to multiply it with. We will get this formula in the exam. I'm just going to say this honestly. Like back in high school, we had like some of the longest formulas we ever need to know. Like I'm sure you had this too, like sine and cosine and how you turn sine into cosine. You have to memorize all these things and like just memorize it. Like it's just n factorial and d factorial then n minus d. Like just in case you don't get it, just memorize it. It's not that difficult. So let's go back to this. So how do we find out the combination? How do we find out the number we're gonna put here? All right. So here's how we do it. We do combination of 3. We just did it, but like I'm gonna do it again. So it's gonna be 4 factorial over 3 factorial into 4 minus 3, which is 1 factorial. So you can just cross this out. This will be 24. This will be 6. So 24 over 6, that'll be 4. And that's our answer here, right? 4. Right? So does everyone understand this? Yeah, it makes sense. All right. So all of you are getting it. So, okay. Now, I want to ask you all a question. And please, this question, you'll answer it based on your understanding of the previous lecture about probability. So here's can you use the sickle cell example? We are using the sickle cell example. What do you mean? Like we just named the children Batman and Superman. We are using the sickle cell example. Like what exactly do you want from the sickle cell example? Like if 2 children are affected. Okay. All right, you guys are all right. So here's the question. Let's say you have forget Spider-Man. We have the 4 children. Okay, so here's the question. Please, I want you to think. Just think for a little bit, okay? And then don't just blurt out the answer and it gets wrong or something. Think about it and then put the answer, okay? So let's say you calculated what's the chance of 0 children being affected, and what's the chance of one child being affected, and what's the chance of two children being affected, and what's the chance of 3 children being affected, and what's the chance of 4 children being affected. Now let's say this probability was, for example, we found that it was 0.3, and this probability was like 0.4, and this probability maybe it was, I don't know what we got, maybe we'll get like 0.2, yada 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 yada. Now if you add all of these, what do you think the answer is going to be? What do you think the answer is going to be? Let's say we added all of these. All right. You know what? I'm going to leave because you guys are clearly the probability experts. So see you guys. I'm just joking. I love that all of you are saying 1. Now, if Does anyone not understand why it's 1? Basically, that is all the possibilities. They either, so for example, it's the same question as saying, when you roll a die, what's the chance of getting 1 or 2 or 3 or 4 or 5 or 6? It's the same exact question. So the answer to this is 6 out of 6. The answer to this is the exact same. You add all the probabilities, and since that's the entire possible outcomes, it's going to be 1, right? It's going to be 1 because either they're going to have 0 children getting affected, or 1 will be affected, or 2 will be affected, or 3 will be affected, or 4 will be affected. There's no other possibility. So you're certain that the probability of none, or all, or 2, or 3, or 4, or 1, whatever, you're certain that if you add all those probabilities, you're going to get 1, right? So with that said, you guys should be the masters of binomial distribution. That's what binomial distribution is. But these are different events, right? Yeah, these are different events. If the chance, one event could be one child getting affected. The other event could be two children getting affected. So they're all different events, but remember, I'm saying either or. All right, here's a good question. You probably already understand where I'm going with this. What's the chance that only one child gets affected and 3 children get affected? All right, does anyone, what's the chance that one child gets affected and 3 children get affected? Exactly, it's 0. It's 0. No. What's the chance that only one gets affected or only 3 get affected? It's 0. There's no way that only 1 gets affected and a chance of 3 also getting affected. It's impossible. So the answer is 0. You got it, because I used and, not 0, not or, right? So did you get that? Did you appreciate the difference? Here I'm saying, no, what's the chance of none getting affected, or 1 getting affected, or 2 getting affected, or 3 getting affected, or 4 getting affected? So you add all the probabilities, and since that's the entire sample space, if you add them all together, you'll get 100%. It's like, what we talked about last night about adding the probability and its complement. It should be 100. So they are mutually exclusive. Yeah, they're mutually exclusive. You can't have one child being affected and 3 children being affected. It doesn't make sense. You can't have only one child being affected and also only 3 children affected. They're mutually exclusive. Either one child's affected or 3 children are affected. Yeah, so they're mutually exclusive, so it has to be 0. So you see, this is why I'm saying, read the question. He could trick you like that, and you could spend the whole time calculating when the answer is just 0, and there will be an answer that's 0. You probably won't even look at it because you're like, oh, it can't be 0. Like, let me calculate everything, and you're calculating and everything, and then the answer is 0. So don't fall into this trap. Read what the question's saying. The question sometimes seems weird, but when you think about it, that's the only answer that's applicable. So did you appreciate the difference? Does this make sense? Yeah. All right. So we're gonna do this one more time. So we're gonna do binomial distribution one more time. I'm gonna show you. We're gonna actually calculate, and I'm gonna show you once we add them all, they should be very close to 100. Now, since we're rounding and things, it might just be 99% or maybe 101%, whatever. The point is, we're gonna do it all in one go. And we're going to see what 0 and 1 and 2 and 3 and 4, and I'll show you how you need to do all these together. And we'll do this. How do you reach 0 mathematically? The thing is, you can't reach it mathematically. You reach it through applying rules. For example, how do you reach 1 divided by 0 mathematically? No, there's a rule that says, 1 over 0 is going to be undefined. And how do you reach, for example, 0 factorial mathematically? No, it's just a rule. 0 factorial is 1. All right, so you can't reach 0 mathematically. It's a rule. If you have probability A intersecting probability B, but they're mutually exclusive, it's 0. It's a null event. That's a rule. So you don't have to calculate it mathematically. You can't calculate it mathematically. Yeah, exactly. So did this make sense? There are some rules. Math is weird, but it's interesting as well, especially when it comes to 0. Like 0 is just 0 is a weird number. Point is, let's now do the binomial distribution. So here's the question. The question might not come in the fashion of sickle cell, but it might come in with another autosomal recessive disease, and the whole idea is the same. The change is 25%. But do you guys want to do the same example, or do you want us to change the probability? Do you want us to change the probability maybe to something like half and half, or do you just want to do the same example? Right, change. All right, so half and half is good, or do you want to do the opposite? Do you want 75% chance of being affected? Right, so we'll do this example, then we'll go Priyasa. Okay, 50-50. Let's do 50-50. So here's how you should do it. I'm going to do it just the way you're supposed to do it in the exam, but now you actually know what you're doing. You don't just plug in these numbers and just have no idea what's going on. So a couple wants to have 6 children. 6 children. All right, I'm making it even harder. So you know, we're going to do 6 times 5 times. Oh, it's fine. It's fine. A couple wants to have. We're going to. You know, if we do 6 children, we might not pay us on time. So let's do 4 children. Let's do 4 children, just to make the math easier. All right, so a couple wants to have 4 children, so I'm going to name them A, B, C, and D. B. Okay. So here's what you do. You know the probability. The probability is going to be 0.5 of being affected, 0.5 not being affected. Now 0.5 kind of makes all the math easy because what's the complement of 0.5? It's 0.5. So I don't have to keep doing 0.5 times 0.5 times 0.5 times 0.5, yada, yada. I only have to change the number on the side. So maybe 0.5 is not the best example, but let's do it. Why not? So what's the chance of none of the children being affected? It's going to be 0.5 to the power of 4, right? Times 1. Because how do I find 1? I just did it instantly. I did 4 factorial over 1 factorial into 4 minus 1 factorial. So this will be 4, right? This will be 4 times 3 times 2, right? 4 times 3, yeah, this will be 24. And then 1 factorial, 4 minus 1. 3 times 2, it'll be 6. Oh, no, wait, no. Why am I using 1? I'm using 0. Sorry, I'm using 0. So this is 0 and this is 0. Yeah, none is affected. Yeah, I made a mistake. See, this is why I'm telling you, and in the exam, when you calculate, just flag and solve it, then go back to it, because you might very easily make a mistake. So 4 factorial over 0 factorial into 4 minus 0 factorial. This is going to be 4 factorial over 4 factorial. So it's 24 over 24. 4 factorial over 4 factorial equals 1. That's where I got the 1 here. Right? So whatever this is, it'll be a certain number, and that number is your answer. Right? Now let's do if 1 child's affected. So what's the chance of 1 child's affected? So now I'm going to do the factorial thing first, because this will just be the same, 0.5 into 4. Because remember, the chance of being affected is half, and the chance of not being affected is half. So this happens to be a coincidence where it's always going to be 0.5 out of 4, right? It's always going to be 0.5 out of 4 and always going to be 0.5 out of 4. So what's the chance of 1 child being affected? It's 0.5 to the power of 4 times a value. So what is that value? It's, yeah, it should be 4, but I'm just going to show how I got it. 4 factorial over, now I'm using 1 factorial because 1 child affected, into 4 minus 1 factorial. It'll be 4 factorial over 3 factorial. So this will be 24 over 6. Divide them, you'll get 4. So this number is 4. Let's do it with 2 children affected. You'll do the same thing, but this will be 2 and this will be 2. So it'll be 24 over 2 times 2. This will be 4. So this will be 6 and this will be 6. Then you'll do it again. And you know, if you do it again, you'll actually get this number. All right. And if you do it again, you'll actually get this number. This is because there's something called Pascal's triangle, and it's in the slides. So I'm just going to show it to you. If 3 children are affected, this will be 3. This will be 3. This will be basically 1 and 3 factorial. So 4 over 4 factorial over 3 factorial. It's going to be the exact same as the first one. 24 over 6 is going to be 4. So this will be, like I said, 4. And then this will be pretty much just 1 because of all of them being affected. It will be 4 factorial over 4 factorial into 4 minus 4. And remember, this is going to be 0 factorial, which is 1. So just cross that out. 4 factorial over 4 factorial, this will equal pretty much 1, and that'll be 1 down here. If you add all of these together, what's going to be the answer? Or not these values, but like these values that you get, what's going to be the answer? This answer, if you add them all together, it'll be 100%, right? Theoretically. But if you keep rounding, like let's say you got 10.52. When you get rid of this 2, maybe when you add them all, you'll get like 99.8. This is because you've been rounding, not because of a mathematical error. But theoretically, if you were not to round and you were to add all the numbers, you're going to get basically that. So yeah, So right now we finished it. Let's actually have a prayer break and we'll get back to it. Yeah. So how about 3:15? 3:15. Is everyone good with 3:15? Why do we multiply 0.5 by 4? Because if you have 4 children, look, it's lucky for, I don't know why we picked 50-50, because 50-50 means that 50%, like what's the chance of being affected at 50%? What's the chance of not being affected 50%? They happen to be equal. So it doesn't matter how I put it. It could be 0.5 times 0.5 times 0.5. When it was 0.25, it was a little more tricky because I couldn't, they weren't just all equal. Some of them were 0.75, some of them were 0.25. But when they're all 0.5, it's fine. I don't have to think about it too much. I just put 0.5 and to the power of 4 because it's going to be 0.5 times 0.5 times 0.5. What did we add at the end so that all became 1? Basically, when you find the answer to this, right, 0.5 times 1 and then 0.5 to the power of 4 times 4 and 0.5 times to the power, when you find the values to all of this and you add them all together, you're going to get 100%, right? And I'm kind of too lazy to actually do all of them together, but you get the picture. But it's not always 1, right? Yeah, look, it's theoretically supposed to be 1. The reason it doesn't end up being 1 is because you keep rounding the numbers. Like when I find the answer to these, what happens is I get 10.52. So there's actually like a lot of numbers back here, but I don't take them. The reason I don't take them is because I just want to make the number very easy. When I omit these numbers, I'm rounding, and when you round, you might face a problem where you're missing a few numbers from here. Yeah, because lots of examples they're almost 1. Exactly, yeah. They're almost 1. They're almost 1 because we keep rounding because we're not going to put in every single number. But theoretically, if you put in every single number, it'll be 100%. So yeah, let's go have a prayer break. I'm going to go pray and come back. And 3:15. Let's meet again at 3:15. I have one. What's the chance to have 1 child affected or 3 children affected? Is it going to follow what you just said now or the union? No, yeah. So, okay. So I like this from Tasneem. What you do is you find the probability of 1 getting affected, right? And you find the probability of 3 getting affected. Then you just add them together, right? So remember, where was the example I did? Yeah. So this was of 0 getting affected. This was 1 getting affected. This was 2 getting affected. This was 3. And then down here where there was 4, where I pointed down here at 1. So you find this probability and you find this probability, then you add them. That's the probability of only one getting affected or 3 getting affected, right? It'll be these 2 things. In the first example of sickle cell, the chance of the 1 getting affected and 3 getting affected, you told probability is 0. How? Yeah, Bushra, the reason it's 0 is because you can't have only 1 get affected and 3 getting affected. These are mutually exclusive. If I said 1 getting affected or 3 getting affected, then it's fine. Mutually exclusive things can happen if there's a union. This was yesterday's lecture. See, this is why it's really important for you to know yesterday's lecture to understand this lecture. So the reason I did that is because of that. So yeah, can unmute. I found the question. Yeah, please tell me, because I think I don't know what this question is. It sounds like there's a trick inside of it. I don't know.
Okay, assalamu alaikum.
Alaikum assalam. Ahlan.
أهلين. يقول لك the question is the average number of surgeries per day in a hospital are 4. Find the probability that on a given day 5 surgeries are performed.
Does he give you standard deviation, anything?
لا, the options are A 1.1563 or B 0.1563 or C 0.1 or D 0.1862.
The average is 4. Honestly, don't know how to answer this. If the average surgery, the way he says the average, it makes it seem like you can have more than the average or less than the average. So I expected there to be a probability or anything else beside it. Because him telling me that the average is 4 doesn't help. I have to have either a probability with it or a standard deviation. Was this a collected question or was this like a Moodle question?
No, this was a browsing question. I found it on the internet.
Oh, I have no idea, to be honest.
يعني there isn't a formula. طيب, there's a similar question هنا برضو. It says يعني 3 out of every 7 patients reporting in the emergency of a hospital are females. What is the probability of getting 3 female patients if 6 patients are selected?
What's the probability of getting 3 if 6 are affected? And every time it's only 3 out of 7. So there should be a way to calculate this. Yeah. So it should be if we have 6 slots and the chance is 3. This is the same as binomial distribution. So just repeat the probability. So for female, it's 3 out of 7, and you want to pick 6.
6, and what's the probability of getting 3 female patients if 6 patients are selected?
All right, so it's going to be 3 out of 7 times 3 out of 7 times 3 out of 7 times 4 out of 7 because the rest have to be, I'm assuming, males, right? Does it say at least or only 3? Because it makes a big difference if it's 3 or at least.
No. What is the probability of getting 3 female patients if 6 patients?
Yeah. So then this is the multiplication we're working with, but now we have to do the combination because, right, it could be the first 3, it could be the second 3. So what we do is we do combination 6, 3, and then it's going to be 6 factorial and over 3 factorial into 6 minus 3 factorial. So it's going to be 3 over 3. I need to calculate for this. It's going to be a lot. 3 factorial. So 6 times 6, we know the bottom one is going to be 36. But what's the top number? We need to do a calculator for it. So it's going to be 6 times 5 times 4 times 3 times 2, 720 over 36 divided by 36 equals 20. So the answer should be, times 20. This is plus, sorry. So this should be the answer. I don't know. Like, I need someone to confirm it because I'm not. I want an iPhone. I can't like do 3 over 7 and stuff. So whoever has a calculator, check this and find the answer and tell me if it's one of the choices or not, because this should be the answer. On average, the number of surgeries and what's the probability there? Look, for the surgeries question, I want you guys to ask Dr. Hassan about this. I have no idea, to be honest. All right. I don't think exemplify. All right, just 1 second, because we're supposed to be starting like 5 minutes ago. Let me just check the last bit of questions, and then we'll see. Yeah, where you asked us to calculate and it adds up to 10. Or 1. I'll repeat that. Can you solve it, please? The surgery one, I have no idea how to even begin solving it. Like if it's, I don't think it's something that's very simple to answer, because if the on average 4 surgeries per day, what's the chance of 5 being done? This is like, I need something to help me. I need like probability or something. I'm sure there's a way to solve it, but it's not part of the stuff that we learned, so I'm not quite sure how to start with solving it. This is different. What is the question again? Yeah, what is it? All right, so the one we solved here, it said if on average every 7 visits or something, every time you see a lady in the emergency department, you see 3 out of 7 ladies in the emergency department. What's the chance that out of 6 people that you randomly pick out of them, 3 of them will be females? It's the same thing as saying if you have 6 children and the chance of them having sickle cell is 3 out of 7, what's the chance? So it's practically the same thing, You just do 3 out of 7 times 3 out of 7 times 3 out of 7, 4 over 7 times 4 over 7, 4 over 7, and then pretty much just multiply that by the number of combinations. And in this case, we have 20. Yeah, can we start? I'm going to start soon. I'll write it here. Let's start off here. I'll do it. I think it depends on the options. I mean, 4 is okay. Does that make sense? Look, the serious question. This is just my tip. Don't scour the internet for too many questions, because sometimes the internet doesn't know what you took. The internet doesn't know what curriculum you took. The world of probability is filled with a lot of things that I don't really want to know. So you don't really need to know too much about that. The average number of surgeries per day in the hospital are 4. Find the probability that on a given day 5 surgeries are performed. Yeah, again, I have honestly no idea. So just ignore that. We really don't want to confuse anyone. And yeah, and like probability, it has a lot of things. It has a lot of things into it. I remember back in grade 10, we had this one type of question where it's easy because the concept's easy. But the problem is that he asks it in a way where we have to answer the whole page and the back page. It was a question that's like, there are 12 rings in a shop, what's the chance that at least one of the rings will be red? And like when you bring in at least, that's just the word that makes the entire problem like this long, because it's, we know the concept, you have to do this, this, and this, and this, but from the amount of work you do, you're probably going to make a mistake throughout of it. So, you know, probability, I know, is, it's not just, you know, as simple as intersection and union. There are a lot of things. We're just taking very, very basic probability so that we can understand these things. So don't wrap your head too much around the surgery question. I'm sure there's a way to solve it, but not one that we can do with the, you know, basics that we learned. All right, so we're gonna do, here's what we're gonna do right now. We're gonna do one binomial again, and since everyone's asking about the 100%, we're gonna, I'm gonna actually get the values. So we're actually gonna do this like legit, and I want someone to help make sure that I didn't make a mistake. So I'm gonna use my like iPhone calculator. So it's, I don't have fractions and stuff, and I might just make a mistake from how I'm typing everything in. So if I make a mistake at any point, just someone stop me. All right. So let's start. We picked half the last time. I think that was a bad mistake. Like it was a bit of a mistake. So do you guys want to change the probability or what? Yeah, let's do 75. All right, 75 is nice. So the chance to be affected is 0.75. The chance to be normal is 0.25. It's the same, it's just we're flipping it. Instead of 0.25 being affected, it's 0.75 that's affected. So let's isn't it? Yeah, it's similar to the first one. The only difference is that we swap them. But the reason I'm doing it is like we're not focused too much on the numbers, just the concept, right? So I'm gonna do this one like completely legit. Let's erase everything. I'm gonna put it up here, 0.75 to be affected, to have the disease. Yeah, we can differentiate between the affected and unaffected this way, exactly. So let's do it. So we're gonna use 4 children because we don't want to make the math too difficult, because I want to go through each and every single one. So it's gonna take a while. So let's say 4 children. So we have A, B, C, and D. So what's the chance that 0 of these children are affected? All 0, you know, none of them get affected. It's going to be 0.25 to the power of 4, right? Instead of just writing it over and over again. And then we need to multiply by something. So what is that something going to be? It's going to be 4 factorial. I'll just write it over here. 4 factorial over so 4 or no, this will be 0 factorial into 4 minus 0. So it's going to be 4 factorial over 4 factorial. You just cancels it out. It'll be 1, right? So this will be 1. Now let's find out what this is. So I'm going to 0.25 times 0. Times 0.25 times 0.25 equals times 1. So what I got was 0.039. Now I'm going to try and keep as many numbers as I can. 0.039, right? So 0.039. Now let's do the next one. It's going to be 1 child being affected, right? So it's going to be 0.25 to the power of 3, because that's everyone that's not affected, and then multiplied by 0.75, the one guy who is affected. Remember, we're using 0.75 as the affected, not like 0.25 with the sickle cell disease. Then we need to multiply by a number. So what's that number going to be? We need to figure it out from here. So 4 factorial over 1, since we want 1 child being affected, into 4 minus 1, which is 3 factorial. So 4 factorial over 3 factorial. It's going to be 24 over 6, right? So 3 factorial is 3 times 2. So this will be 4. So that means this will multiply this by 4. So can we have someone figure this out? 0.25 times 0.25 times 0.25 times 0.75 times 4. So I got 0.0469 exactly. 0.0, it's like 46875. We're kind of rounding, so we're already like 0.04. I'll just write it all, just because I don't want to round. 6875. Okay. So that's the second answer. The next answer is going to be 0.25 to the power of 2, 2 of them being normal, while 2 of them being affected. So 0.75 to the power of 2. And then we got to multiply by a number. So what's that number going to be? It's going to be 4 factorial. I'm just going to do it here. 4 factorial over 4 factorial over 2 factorial into 4 minus 2 factorial. So this will be 2. 2 times 2 is 4. This will be 24. 24 over 4 is going to be 6. So this will be 6. So let's find what that is. 0.25 times 0.25 times 0.75 times 0.75 times 6. All right, so I got 21. So 0.211. Yeah, all right, we're rounding. It's fine. 0.211. All right, well, it's fine. It's fine. We'll round. So long as we round up, we won't lose marks, right? We won't lose points, so it's fine. Now the third one. So 3 getting affected. So that's going to be 0.25. Only one person will be all right. So this is power to the power of 1 into 0.75 to the power of 3. 3 getting affected. So this, I can just apply Pascal's triangle because this will be the same as this. But I'll do it here for you just so you know. 4 factorial over 3 factorial into, what was it? 4 minus 3, which is 1 factorial. This will be times 4, right? Because this is the same thing as we had here. 4 factorial over 6, 24 over 6, which is basically 4. So this is 4. And then this will be, let me just make sure, 0.25 times 0.75 times 0.75 times 0.75. So it's 10.5% times 2, right? Times 2. Times 1, times 4, sorry, times 4. So yeah, 42. So 0.422. I'm gonna, yes, I don't want to round down. I'll do 0.422 to round it off. And then last but not least, it's 0.75, all of them getting affected, right? 4 times a number. So that'll be like 4 factorial over, I don't know, like 4 factorial into 4 minus 4, which is 0, which is going to be 1. So just cancel it. So it's going to be 24 over 24. So it's going to be 1, right? So this will be 1. Yeah, that's actually a pretty nice remark from Muhammad. If you add all of these and just minus them by 1, you'll get the last one because it's the last one, right? So yeah, that's a good one. But we'll just do it just because we already did all this. So times 1. So what's 0.5 times all that? 0.75 times 0.75 times 0.75 times 0.75. It's 0.3164. All right, now let's add our 4, 1. Let's now add all these together. So it's going to be 0.0039 plus 0.046875 plus 0.211 plus 0.422 plus 0.31641. And look at that. I mean, it's close enough, but it's 100%. And it should, of course, be 100%. In fact, let's do what Muhammad said. Let's actually add these and then subtract them from 1. Let's see what we get. We'll get 0.0039 plus 0.046875 plus 0.211 plus 0.422. Now that's the number I'm stuck with. So I'll just do minus 1, and it'll be negative, but it's fine. Look at that, 0.316, it's because they're rounding, but like, you get the picture. Yeah, it's exactly 1, adding them all together. Yeah. If no rounding, yeah, of course it'll be 1. The problem is the iPhone also doesn't show you the numbers after that. So eventually the iPhone itself rounds, so even if you try and get every number the iPhone tells you, at the end of the day, you're not going to get it. So point is, this is how we solve binomial distributions, right? So all of you now know this, right? All of you are good with this, and this, if you get a question on binomial distribution, it's a gimme question, right? Just make sure you flag it, you go back to it to make sure that you don't, mess anything up. Now, now it's time we learn more theory about the binomial distribution. So for example, look, there is a formula for this, but I'm going to prove to you that you know math. I'm going to prove to you that you, by yourself, you actually know math. So let's say a couple wanted to have 4 children, okay? And let's say the chance of having sickle cell is 0.25. So on average, how many children will have, if you have like 1,000 couples that have 4 children, on average, how many children will have sickle cell disease? If you're going to have 4 children and the chance is 0.25, what's the chance that, or what, on average, how many children will be having sickle cell on average if like 1,000 couples do it and get 4 children? All right, everyone's saying 25%. No. I'm telling you 25% is the probability. Right. Okay. If you have, let's say one couple comes to your office, there are 4 children. On average, how many of these 4 children will have sickle cell? Yeah, 1 child out of 4. You want to know what's crazy? I didn't even need to tell you this. So 1 out of 4. So on average, 1 child will be affecting it. The formula, guess what? It's actually this times this. So look, I didn't even need to tell you the formula, and you already know it. It's if you multiply 4 times 1 out of 4, this cross, you'll have 1. So on average, 1 child will be affected. So you see, like, you didn't need to know the formula, but for any binomial distribution, the way you find the mean is just n, which is the number of children, times p, which is the probability. So you did that by yourself. You don't need a formula. If he asks you in this binomial distribution, what's the mean? You don't need to be like, oh my god, mean. What do you mean mean? Like all I took was this stuff. What do you mean mean? I don't know what mean is. No, you know what mean is. Mean is just this times this, right? So mean is 4 times 0.25, n times p, right? So we're gonna go over the slides now. I really hope the calculation side of it is really clear, and he will ask you. About this. So let's stop this and let's go to the actual presentation. So yeah, now it becomes very easy. So he's telling you, oh, here the heterozygous. Let me actually bring the chart up. If we multiply the probability with the population size, we get the same thing. Yeah. So if you have, for example, 1,000 people in a population, right, and they all have 4 children, and all of their chances are 0.25, then what's like on average, how many people will have 1 child, or on average, how many children will get affected, or how many? This is kind of stupid. Like if there are 4,000 children, right? 4,000 children, because 1,000 families, 4,000 children. How many will get affected? Then basically 1,000 will get affected, right? Because it's 1 in 4. If you have 1,000 children, so 250 couples, then 250 will get, yeah. Mentioning others, I mean like mentioning the other. Yeah. So here is where he asks without mentioning others. I kind of don't get what you mean, but look, we'll go over the slides. It'll make a lot of sense. So for multiplication rule of probability, you remember that, hey, the chance. So his chance of giving his bad chromosome is half. Her chance of giving the bad chromosome is half. So half times half, you get 25%. This is just another way. I did the Punnett square, which is the exact same thing, right? 50%, 50%, so you get 25. So he found it a different way. I use the Punnett square to find the 25% chance. If we say mean for every 5 times 0.25, yes, but the thing is, like 5 times 0.25, it'll give you like a decimal. So like I made the math easy by giving you like 4 and 0.25, right? So he'll give you like numbers that are easy. But yeah, the mean is going to be like, I don't know, 1.25, something like that. So yeah, so like 1.25. And that kind of does make sense. Like 1 and every quarter family, like for every 4 families, they'll have an extra 1 being affected, right? So yeah. Like if every family had 5 children, there will be a lot of families that have 4, like only 1 will be affected, but every 4 families they'll have 2 getting affected because there's 1.25, right? 25. Every 4 families, this 25 will start adding up until there's 1 extra person. So it's mean times probability. Just remember that. So again, he's just giving you everything. The probability of not having sickle cell, the complement is 1 minus 25, which is 75%. So it makes sense. You guys know this. So binomial means there are 2 possible outcomes. Either they have sickle cell or don't have sickle cell. Moreover, there's an important assumption with a binomial. There are a fixed number of n. So fixed number of children, like 4 children, 3 children, 2 children, so on and so forth. So you need to keep this in mind. When he's talking about a binomial distribution, there are 2 really important assumptions. One of which is that, there are only 2 outcomes which are mutually exclusive. Either you have sickle cell or don't have sickle cell. And the n is fixed. You can't have 4 children and then one family has 3 children, one family has 2 children. No, all families need to have 4 children. So that's how you find the probabilities. So yeah, if a couple have 4 children, what's the chance that none of them have this? The parameters describe this. What's p in this example is probability. What's n in this example is the number of children. We talked about this. So yeah, here he's describing to you how you find the probability. But hold on, if one is diseased, then it could be the first one, the second one, the third one, the fourth one, which is why you need to multiply by 4. Right here, you need to multiply by 4. So this is everything that we talked about. What if there are 2 diseased? Well, now there's 6. You know, there's I feel like I'm a broken record here. Just keep on repeating. So there's 6, so you multiply by 6. And then this is Pascal's triangle. Basically, as you keep doing more and more combinations, you're going to notice that it's going to go up. And then as you reach the end of the combination, it's going to keep going down. So it's a perfect sort of triangle. And you can memorize the triangle instead of just doing the combination, but just do the combination. You don't want to just memorize and then end up forgetting during the exam, or there's the coffee just hit you too hard or something. And yeah, so I recommend just knowing the actual formula instead of just using Pascal's triangle. But the idea is that, remember how I went from 1 to 4 to 6, and I told you, hey, look, it's going to go back to 4, then back to 1. That's Pascal's triangle, where as you keep increasing the combination of the number of people diseased, is going to end up going back to the actual normal value, the values you started with. And then here he's showing you how, hey, look, if you actually calculate this probability and this probability and this probability and this probability and everything, and hey, if you add them all together, you'll get 1. Now notice, since he's working with 25, he's getting here 31%, but here he's getting 0.03. We actually had the opposite. So since we were working with 0.75 instead of 0.25, we actually got this number here, right? And it makes sense because we flipped everything. And this number was here, and this number was here, right? And everything was flipped. The only number that was the same was in the middle. But that's important. When you modify P, notice how the bigger values, they get sort of shifted, right? They get shifted and the other values go to their place. This is important because notice, if we go here, look, when you increase P, the same thing we did, the actual whole graph will shift to the right. And this is really important. He will bring you, like, this is a theory question. He'll tell you in the exam, if you have a binomial distribution and you increase P, what will happen to the graph? And he'll have shift right, shift left, narrow, gets wider, or nothing changes. And the answer should be, if you increase P, it's going to shift to the right. If you decrease P, it'll shift to the left. And you just saw it. Notice how here the probability is half. It's going to land on 2 because remember the mean, the average, this thing here in the middle, the average is going to be 4 times half. 4 times half is what? 2. But notice when you increase P, the mean is going to go right here. It's going to be shifted to the right. You get it? So the same thing happened with us. He used a P of 0.25, so his mean was here. But when we used 0.75, our mean was here. You get it? So he shifted everything to the right. So remember this, increasing P shifts things to the right. Decreasing P shifts things to the left. Increasing N makes things narrower. All right, so I know it doesn't look like it's narrower, but it actually is narrower. You just have to trust me. It makes things a lot narrower. And when you decrease N, you actually make things a lot wider. Now, this is a general rule in biostats. Whenever you increase your sample size, whatever the distribution you have, it's probably going to get narrower. And we'll talk about that in the next lecture. But keep this point in your head that, hey, increasing P, shift to the right. Increasing N, it's going to get narrower, right? So here are the assumptions that I talked about. Probability has to be constant, right? The N has to be fixed. It's either 4 children, 5 children. You can't just have one couple has 4 children, one couple has 6 children. N has to be fixed. And the outcomes have to be mutually exclusive. The outcomes are independent of each other. In other words, that if the first child is affected, doesn't affect the probability of the second child can still be affected, yada, yada, yada. Probability is constant. So we talked about all of this. Now here's the important part. Combination, memorize this formula. It's not that hard. Number of children, disease, right? And then just apply it, right? So I really hope you just don't forget this. And remember, 0 factorial is 1. 0 is just a weird number. Actually, there is a reason why 0 factorial is 1, and it is a pretty interesting reason. Basically, here, I'll do it here for you. 4 factorial, what's this? Yeah, increasing N makes it more narrower, and decreasing N yeah. So look, I'll show you why 0 factorial is 1. There is a kind of a reason for it, but it's more of a pattern thing, not really. So look, 4 factorial is 24, right? 3 factorial is 6. And if I find 5 factorial, can someone find 5 factorial? It's 24 times 5. So what is 24 times 5? It's going to be like 120? Yeah, 120. Okay, so 24 times 5 So it's going to be 120, right? And then 2 factorial is going to be 2. And then 1 factorial is going to be 1. And then 0 is going to be 1. So how can you prove this? Look, 120, if you divide by 5, what happens? Divide 120 by 5, you're going to get 24, right? So now divide 24 by 4, you're going to get 6, right? So divide by 4, you're going to get 6. Divide by 3, you're going to get 2, right? Divide 6 by 3, you're going to get 2, right? So this is by 3. Divide 2 by 2, you're going to get 1. Well, then what's the next pattern? It's going to be 1 divided by 1. And what's 1 divided by 1? It's 1. So although 0 kind of messes up everything, there is actually a sense to 0 factorial being 1. So don't forget this. Don't forget this idea that 0 factorial is 1, because you might get it. You might get n minus d. This might be 4 minus 4, and this will be 0. You might say this whole thing is 0 and this is undefined. No, 0 factorial equals 1, right? So don't forget this. All right, look, every single time I explain this slide, everyone always goes insane. And I don't think there'll be a difference right now. Look, back in grade 10, you probably learned there are 2 different things. There's combination and there's permutation. Did you ever take that? I just want to see if people took that. All right, some people didn't take it. It's fine, it's fine. So look, I'll just quickly explain it. Permutation means that not only is the person who gets affected important, but also the order is important. So for example, remember when I said Batman, Superman, and Iron Man and Spider-Man? So what permutation does, it says not only, so let's say one guy gets affected. What I said was, first time we did it as Batman, then it was Superman, then it was Iron Man, then it was Spider-Man that gets affected, right? And then the others are not affected, right? Others are not affected. What permutation says, it says, no, I'm going to go one step further and also say Batman has to be affected and he's the second child, or he's the third child, or he's the fourth child. We don't care about this. So he's just telling you here, he's just telling you, we don't care about permutations. Permutations care about the order. So for example, I'll show you where this matters. This matters back in grade 10 when there's a word problem that says little Timmy is on his iPod and he wants to listen to Taylor Swift, right? And then he wants to listen to Metallica, and then I don't know, like a third Ariana Grande, all right? So he's like, how many different orders can you listen to music in? So the question is telling you, don't calculate combination, calculate permutation. So how do you do that? You just do 3 factorial. It's literally that easy. You just do 3 factorials. It's going to be 6. So there are 6 different ways he could listen. He could listen to Taylor Swift first, and then Metallica, then Ariana Grande, or then Metallica, then Taylor Swift, and so on and so forth. But the idea is that we're not going to use this here because we don't care about the order. Combination, what combination says is that I don't care if he's going to listen to this or this or this or this or this. I just care that he's going to listen to all 3. So there's only one combination of listening to all these 3 songs, but there are 6 permutations. All right. Here with the children, it actually makes a difference if it's Batman or Superman or Iron Man or Spider-Man. But I don't care if Batman was affected and he was the first child, or Batman was affected and he was the second child, or Batman was affected and he was the third child, or Batman was affected and he was the fourth. I don't care. It's the same person. It's Batman getting affected. I only care if the child actually changes. If the child is not, if Batman gets affected and then it's Superman getting affected, right? So you get this idea, right? So all he's telling you here is don't use permutations, just use combinations. So it'd be like 3 factorial over whatever, 2 factorial into 3 minus 2. But use combinations. Don't use permutations because we don't care if the order is different. We just care if the person is different. If the person is different, then yeah, there's a different combination. So yeah, that's what this slide trying to tell you. So although there are 6 orderings to A, B, and C, it's still just A, B, and C, right? Although you have Batman affected and the rest are normal, putting him as the second child, but he's still affected, it's not going to make a difference. If Superman's affected, yeah, it does make a difference. But if Batman is still affected, but he's the second child, it doesn't make a difference. So that's what this slide is saying. Do you need to know permutations? Well, now you do, but no, you still, for the calculation side of it, you still use combinations. So again, he shows it to you. What formula was, yeah, you just do, so what formula was for permutations? You just do the number factorial. If you have like 4 children, how many different ways can you order them? it's 4 factorial. So you can order them in 24 different ways. But the combination, assuming one is affected, is going to be like, I don't know, 4 factorial into 1 factorial. You get the picture. Like you get the picture. You're going to use this, right? So forget the permutation formula. It's literally just a number and factorial. That's the formula for it. And this is more like to do with grade 10. He's just telling you here that we don't care about permutations. We care about combinations. You get it? So combinations is what we're focusing on here. So he's showing you again. Notice Pascal's triangle. We're going up and we're going down, right? So this is the same as this, and this is the same as this. Again, same thing. He's telling you here how you can use JAMOV, which is like, I don't know, it's a module that helps you find out the probabilities, yada, yada, yada. All right, now remember how I talked about mean? There are actually other formulas. So this is mean. We took it n times p. But variance, now I'm not going to go into too much detail why variance is going to be np into into 1 minus p. But I will mention this. Here they mention for you np into 1 minus p, and they tell you this is a maximum when p equals 0.5. Now we're going to travel back to grade 8 to explain this and why this is the case. And we're going to use a riddle to explain this, because both ways you can understand this. So I'm going to go to a white screen. Where's the white screen? There we go. All right, so you can see this. All right. I use a lot of slides here. Okay, there we go. So look, this is the formula, np into 1 minus p. Now, do you need to know that this is the way it's understood? No, I'm just using this way to make you understand, because I'm sure you remember this. I'm sure for a fact it's somewhere in your head. But all I need you to know, the main goal of me doing all of this is just remember p is at a maximum at 0.5. That's the main goal of all of this that I'm about to show you right now. So remember back in grade 8 when we had, 1 second, the chat's not showing up. Just 1 second, let me stop and do it again. There we go. Okay, now we got the chat. All right. Remember back in grade 4 when you had parabolas? Remember when you had parabolas that open up like this, and there's a vertex, and then there's other parabolas that open like this? Remember this? Please tell me all of you remember this. Maybe you studied in Arabic, but like remember when you have to draw this, and there's a vertex, and yada yada yada. Yeah. All right. So watch this. Watch this. All right. Y equals np into 1 minus p. Now let's introduce this into the parentheses, right? So it's going to be np minus np squared. Now let's arrange this. Negative np squared plus np. Now we have a quadratic formula. And now you probably remember that this value here, n, it was going to be a, right? And maybe you took it in high school that when you have a negative here, then the vertex opens downward. So when you graph this thing, when you graph it, there is a maximum to this thing, and it's at the vertex. So whatever this value is, this is x, by the way. So if we can find the x value for this vertex, then we found the maximum for this parabola. We found the maximum. And can you guess what the maximum is going to be? It's going to be half. But how can we apply that? Well, basically, remember this thing, how to find the vertex? Does anyone remember how to find the vertex? There's a formula that you used to use in grade 8. Does anyone remember it? I'm really like hitting memories. Yeah. All right, Tariq, man, I'm like really impressed right now. Negative b over 2a. Negative b over 2a. So yeah, this is the formula. So again, what was negative b? Was this? It was n, and a was this, which was basically n as well in this case. So basically, let's just give n any value. Let's give n any value. Let's say n was 4. All right, so it's the formula is negative 4p squared plus 4 p. So how do we do it? Negative b. This is negative b, and this is 2a. So it's going to be negative 4 over 2 into negative 4 squared. Now what is this? Oh, sorry, no, not squared. 2 into negative 4. So it's going to be negative 4 over negative 8. And guess what? It's going to be half. And it's going to be 0.5. So look at that. P-value is at a maximum when it's half. Because this is the point right here. There's no other point in the graph where it's higher than this point, and at the exact x value, or rather the p is going to be 0.5 here, 0.5, and the y can be whatever. We can like solve it later, but we don't care about the y. We care about the p. So does this make sense? Yeah. So this is like a way to sort of correlate what you learned back in high school with this thing that says p is at a maximum of 0.5. There's another way. There's a riddle. So let's say, for example, I'm going to give you any amount of dollars between 0 and 100. But any choice you pick, I will minus it by the opposite. So, or not minus it by the opposite, not minus it by the opposite. I forgot what the exact riddle was. Basically, you're supposed to pick 50 because however way I affect it, you always want to pick the center, because if you pick 100, you're gonna lose 100. If you pick 0, you're gonna lose like the opposite. You get it? So like here, this is the, I think, the riddle, or how you say it. It's gonna be like, pick a number, but I will multiply it by the opposite value of it. So if you pick, for example, 100, I'll multiply it by 0, you'll get 0. So what's the perfect value to pick to get the maximum amount of money? So the answer should be 50, because if the highest point you can ever get is 50 times 50. Even if you get 49 times 51, this will not be as good as 50 over 50. So generally, whenever you have this problem where you're going to multiply something by the opposite value of whatever you pick, you always want to go right down in the center. That's why when you go back to the actual formula, I'll show you the formula, which was NP times 1 minus P. Where's the, yeah, here we go, share. You have P times the opposite of P. So the way P is at a maximum, you have to go right dead in the center between 0 and 1, and it has to be, 0.5. Because remember, P is the probability. It can only be between 0 and 1. So does this make sense with everyone? So if you get a question, I'm not required to know these concepts, right? Muhammad, I had this question in my midterm. It was a question that said the variance, like it wasn't asking about this, but the answer was this. It was saying which of the following statements is true regarding a binomial distribution. Variance is at a maximum at 0.5. That was the answer, right? So that is not tricky. That is something that you need to know and you need to realize. So you're not required to know, why it's half. But when I tell you that it's half, and I give you the parabola reason, and I give you the riddle reason, it sort of makes sense to you. You don't need to memorize it. Oh, now it actually makes sense. Since there's P times 1 minus P, the only way you're going to maximize it is if P is dead right in the center. So now you actually understand why, P is 0.5. If you want to memorize it, memorize it. I don't know. Yeah, so the reasons you don't need to know, but I like giving you the reasons because then it sort of makes sense. So yeah. So if variance is this, then what is standard deviation? It's going to be square root of all this. So that sort of makes sense. And just in case he surprises you, wants you to calculate this, just memorize the formulas, right? So mean is NP, and then the other one is just NP into 1 minus P, right? So just memorize them. And the standard deviation is just the square root of that, right? So that should make sense with all of you, and hopefully that really just is cemented in all your minds. So does that make sense? And the best part is, we said we will provide you, yeah, perfect, your formula sheets, beautiful, perfect. Okay, so we're done with binomial distribution. We're done with the one concept. Now it's the other concept's turn. You're gonna actually be surprised. This concept is a lot easier, right? Much easier. So before we begin with it, I'm gonna go to the whiteboard and we're gonna discuss all of the things about it. Then we're gonna go back and see the slides, because notice how we finish really quickly when we do that. So let me go back to the whiteboard so we can understand it before we actually go through it. All right. So now we finished binomial. Look, this was all about binomial distribution. Now you know it, you understand it. You don't need to memorize and everything. Just revise it really quickly, and you should be good to answer many of the questions. But now we're talking about multinomial distribution. Now you might, it's not Minnesota. You might think it's harder. when we were talking with binomial distribution, we were only talking with a select number of fixed cases, like for example, 4 children. Now with a multinomial distribution, we're considering an entire distribution. So we are supposed to be now in charge of not just one value or 2 values or 3 values or 4 values. We're in charge of an infinite number of values. This distribution goes on forever. It's just that the majority of the point lands somewhere here. So now you might think that, oh my God, how are we going to handle all of these points? It's incredible that this is actually easier to handle than binomial distribution, and it's a lot easier. Now here's the gist of it, okay? If we have one distribution, now let's assume both of them are normal, all right? Let's assume both of them are normal. Let's say the mean here is 10, and the mean here is 100. The standard deviation here, this is sigma, not 6. Standard deviation here is 1. Standard deviation here is 10. This is what people thought. They said, well, if these two are normal distributions, so they're equally symmetric, then that means if I go one standard deviation this way to 110, and one standard deviation this way to 11, then probably if I want the chance of all of this happening, like what's the chance of me randomly picking someone that's 11 or more, should be the same chance as someone who is 10 or more. Do you all agree with me on this? Like, chair absolutely killed me. No, repeat please. Okay, it's fine. Just let me fix my chair. So look, this is kind of a tough topic to explain, but once you get it, it really explains multinomial distribution completely. Let's say, all right, first off, I'm going to show you just how I quickly read curves, okay? Let's say we have a distribution like this. And the mean is 10. And the standard deviation, which is, this is a Greek letter, it's called sigma, is 5. I want you all to answer. If I go one standard deviation this way, what's the value that's going to be here? 15. All of you agree it's 15, right? All of you agree it's 15, right? Now, if I go one standard deviation this way, what's the value that's going to be here at one standard deviation? 5, right? 5. All right, now let's take a different distribution. Remember, they're all normal distributions, correct? Oh, you know what? I just got an idea. Remember lecture number 3 when we talked about the empirical rule and how there's, if you took one standard deviation is going to be 67%. Remember that? Let's apply the same logic. So let's say this was 100, and the standard deviation was 50. If I go one standard deviation here, what's it going to be? 150. And if I go the other way, what's it going to be? 50, right? And then if I go this standard deviation. Now, look, despite the numbers being different, right? These are 10, 5, and 15. These are 50, 150, 150. I made the numbers simple, but we can all agree they're different, right? Despite them being different, if I check the amount of data between this point to this point, if I check how much of the data is here, how much is it going to be in a percentage? It's going to be 67.7%, right? Yes, because it's the chance. We don't care about the values. Exactly. So again, if I check all the data between all of these points, what's it going to be? Again, 67.7% chance. So look, despite the values being different, the percentage is the same. So now they finally understood something. They said, regardless of what values I have down here, if I have, for example, just the mean and the standard deviation, and I'm interested in any point in this graph, I can find out the percentage. Where did 67% come from? It came from the third lecture, the end of the third lecture. We talked about how if you check one standard deviation between the data, the empirical rule, it's going to be, 67% of the data is inside. If you check two standard deviations is going to be 95% of the data. If you check three standard deviations, it's going to be 99.7% of the data, right? So that came from the third lecture. But yeah, so they came up with something amazing. They said, if it's a normal distribution, we shouldn't care what the values are down here. We can always find the percentage. So if I'm interested, so here's what he said. He said, if I'm interested in finding what the chance is for 20 or beyond that, I should be able to find it out, because it's a normal distribution and this is all normal, and I'm going, if I have the mean and standard deviation, I should be able to find another percentage for this. Now, how did they do it? I'll reveal everything. But can we all agree on this concept that regardless of what values you have down here, you can always find a percentage. You can always find a percentage as long as you know the mean and the standard deviation. All right, everyone's agreeing with me. All right. So here's what they said. They said, all right, if I'm interested, let's say, for example, if what's the percentage for the second standard deviation? I'm just gonna write them here so we don't forget. 67, it's 95, and then 99. All right, they have like dots, so this is like 7, this is like 7 maybe, and this is like 7. I don't know, but like that's the gist of it. Move this down here, and then yeah. All right. So look, here's what they said. They said, let's say the mean is 20, all right, and the standard deviation is 5, just to make the numbers easy. They said, if I just know these two, then you can pick any point you want. You can pick any point you want. I will find out the percentage for it. All right. So they told them, we'll make the numbers easy for you. Let's say 25. So what's the chance of getting a value at 25 or beyond 25? All right. So what's the chance of? You all agree with me that it is possible to find this percentage, right? All right. Before saying 33%, don't just try to answer it like straight away. I want you just to think. I want you just to think for a bit. Don't we agree that this is one standard deviation? This is one standard deviation. Let's go one standard deviation this way. Yeah, so let's go one standard deviation this way. So what's the percentage of all of this? 67%, right? Now I want you all to stay with me. All of this is 67%, but I'm interested in this. So let's first minus all of this from 100. What's it going to be? Around 33%, right? 33%. But hold on, 33% is including this part and this part. So now we know that, hey, 67% is here, right? This is, and this going to be together 33%, right? So if we divide by 2, because they're symmetric, then basically 33 over 2 is going to be your answer. It's going to be this area. Did you guys get this? Yeah. All right. Now let's kick it up a notch. You guys understand the concept. But you know what they said? They said there's not really much use in just knowing, for example, 1 standard deviation or 2 standard deviations. I want to know the numbers in the middle. Can we do that? And then one poor guy had to spend all day doing the entire z table. So he said, all right, so if you get this z, then that means that you're going to get this percentage. If you get this z, that means you're going to get that percentage. You're going to get this z, that means you're going to get that percentage. You get this z, you're going to get that percentage. You get this z, so on and so forth. So now all you have to do is find the z. Now what is z? It's number of standard deviations. All right, z is number of standard deviations. Now let me go ahead. I want to actually just copy. I don't want to move this 1 second. I'm going to stop sharing screen for a second. I'm just going to go grab the z table and put it in our whiteboard so that we can use it. Where the hell's the z table? Okay. Kind of surprised none of you want to break so far, but like we'll keep going on. I will put it here, and I'll just repeat what I was doing. All right, and then go here, no, go here, share, go here. All right, so now you should all see. So I got the z table, right? Let me get the pen. Put this up here. All right. So look, Z is standard deviation. You don't believe me? Remember when I said this is going to be, let me actually find out what the actual answer is. 33 divided by 2. Bring up the chats. Right. Didn't we all agree that this is going to be 16.5? 16.5%? We all agree on this, right? Now, this is just us rounding. We're skipping the decimals and stuff. So I'm going to show you how, by using the Z table, I'll get the exact same answer. So look, didn't I tell you Z is number of standard deviations? So let's do this. Let's do this. Here is our distribution. This is going to be, let's say, 10 sigma. We don't care about these numbers. It's going to be 5. So here's what the guy asked me. He said, what's the chance of getting 15 or anything more than that? Right? So I'm going to say, 15. Well, that is going to be 1 standard deviation. So Z equals 1. Right? You all agree that Z equals 1, right? Because Z is the number of standard deviation. So Z has to be 1, right? So if we go to 1, guess what? If 1.0, 1.00, 0.169. The beauty with Z and what it finds, I'll explain to you. Z is the number of standard deviations. Do you know how to read the Z table? Does everyone know how to read the Z table? No. Okay, so look, Z table is really simple. Let's say Z equals 2.7. It's really simple. You just find 2.7 here. Let's say 2.73. You find 2.7 here, and now this is 2.70. 2.7, yeah, 0, 2.71, 2.72, 2.73. Now you correlate the two numbers. So we want this row, right? But we want 2.7. So here's the exact value we want. Now, all of these values, they're all the different probabilities that can happen. The beauty with Z, it always gives you the probability beyond that point. Listen, I'm not saying after, I'm not saying before, I'm saying beyond that point. Meaning that if you wanted a point here, and it was 5, the Z, it'll tell you the percentage is here. You get it? So Z just tells you, hey man, you want a Z of 1, find the percentage, and that percentage is going to be this point or beyond that point. Did you get it? So do you know how to read the Z table now? All right, so you know how to read the Z table. Now let's do our example. Now we all can agree that Z here is 1. He wants this value or beyond that value, right? Beyond isn't on either side. Yeah, on either side. Either if it's on the right, that point or beyond that point, or if it's on the left, beyond that point, or that point or beyond that point. Yeah. So now let's go back to Z. He's interested in this population of getting 15 or more than 15. Now we can all agree this is 1 standard deviation far, right? This is 1 standard deviation far. So we can all agree that Z equals 1, right? Can you all agree with me that Z is 1? Yeah, so now let's go see what 1 is. We want exactly 1.00. So this is 1.0 and then this is 0. So when we go together, we're going to have this value. And guess what? This value is 0.159, which is very close to 16%, which is very close to the value we got. We got this 16.5 because we were just rounding and everything, okay? But the actual value is it's 15.9%, right? So the chance of getting 15 in this population with this standard deviation and everything, the chance is 15.9%, getting that value or beyond that value, right? Can you repeat, please? I'll repeat it, no worries. First off, let's just go back to the first thing we did. Didn't we say that if we go 1 standard deviation here, 1 standard deviation here, then all of this is 67%? Right? We all agree on this, right? Can you do another example? Yeah, we'll do another example. Let me just do this one more time. Let's repeat it one more time. We all agree this is 67%. Now let's say this was 10 and sigma was also 10. So this is 20 and this is 30, right? Yeah, it's the same either side. So so let's say the question said, I want you to find out this percentage. What's the percentage of getting 20 or more than 20, right? So one way we can find it out is just by the logic we learned in lecture number 3, by doing the percentage here, which is 67, and then minusing that from 100, because all this side and this side will be the remaining parts. So if you minus 67 from 100, it'll be 33%. So 33 represents both this side and this side, but we're only interested in this side. So what do? We divide it by 2. Since it's symmetric on both sides, this side has to equal this side, right? So if you do 33 divided by 2, you'll get 16.5, which is very, very close to the number that we'll actually get from the z table, right? The reason it's not the same is because it's not exactly 67.7, it's like 67.7, so it'll be like 33 or 32.3, something like that. So pretty much it'll be different. Yeah, 32.3, and then divide this by 2, you'll get like 16%, something like that, right? Now let's do it with the z table, right? So here's how the question will come. It'll tell you, here's the distribution, and this mean is 50, and sigma is 10. So now what is one standard deviation this way? It's 60, right? So let's imagine the question told you, I'm interested in finding out what's the percentage of 60 or more. What's the chance that in this population you land on someone randomly who is at a value of 60 or more than 60? So we can all agree that this is one standard deviation away from the mean. This is this exact point. It's one standard deviation away from the mean, right? Can people say yes? Yes, okay. So basically, we can agree, since I'm telling you this, z is standard deviation, we can agree that z equals 1, since there's one standard deviation, right? So then all our work is done. We just go and see what is the probability in the z table, since it already tells us the point and beyond. I don't need to do any more work. It by itself tells me that this number you're going to find, it's the percentage of that landing on that value or beyond. So let's go see what it is. It should be same to this value that we got here, since this is practically also one standard deviation and we're finding everything beyond it. So if we go to the z table, if we check 1 and it's 1.0, we'll get 0.159. So it's telling me z is giving me a p-value. I'm introducing this concept to you, a p-value, a probability of 0.159. Get it? We're getting 0.159. And so it's telling me your chance of landing on this number or beyond that number is 0.159, which is 15.9%, which is very close to the value we got, which is 16%, right? So did that make sense? What did the column stand for? So look, when you have a z value, let's say your z was 1.37. You only have 1.3 here. So it could be 1.30, 1.31, 1.32, 1.33, 1.34, 5, 6, until you reach 7. Cam's in the way. So you reach 7. So that's what the columns mean. Get it? The second number after the decimal. Exactly. You get it? So now you all understand how we got 16 using the idea from the lecture number 3, and the idea using the z table, how we got 16% and 16%. Is this, before any questions, is this point clear? Yes. Okay. So some people are saying yes. All right. Now, it's very easy. It's very easy to estimate. Let's do, for example. Now look, I'll make it a little tricky for you guys. All right, I want everyone to answer with me. Let's say here's 100. And sigma is 15. Now, here we go. Ready? What is one standard deviation this way from the mean? 115, right? These are baby numbers, right? What's one standard deviation below the mean? 85. Now, here's the trick. What is, for example, what is 109? How many standard deviations is that away from the mean? How can you know? You can't know. It's very difficult to know, right? You can't really, it's within one standard deviation, but that's not a z value. I want you to tell me z equals a number, like 1 point something x or whatever. So how do we figure it out? Listen, there is a formula, but please, for the love of God, do not just memorize the formula. My friends went into the exam, they're memorizing the formula, and they're making mistakes. Don't memorize the formula. It's such an easy formula, and I'll show you that you even know it. Here, watch. There are 8 pizzas. right? Everyone who eats pizzas, they have an average of eating only 2 slices. So the distribution is they only eat 2, the mean is that everyone eats 2 pizzas, right? Uh, the standard deviation is 1 pizza. So, this is bad. Hold on. Okay. Oh no, for some reason I have to make more pizzas. So let's say we have 16 pizzas, right? 16 slices of pizza. So 16 slices. And the average that people usually eat are, for example, 2 slices. They eat 2 slices. So the mean is 2 slices. And the standard deviation is 2 slices, right? So if someone eats 4 slices, what standard deviation is he at? He's at 1 standard deviation, right? What if that person, get ready for this, what if that person eats 5 pizzas? 1.5. I'm going to tell you exactly what you're doing. All right, here's what you're doing. Are you ready for this? You're not going to believe it, but you just did the formula without even knowing it. You actually just did the formula without even knowing the formula. What you did, I'll show it to you right now. You did 5 minus 2 over 2. That's what you did. And you're not going to believe me, but that's exactly what you did. And you got 3 over 2, and then you said, hey, it's 1.5, right? But you didn't think of it the way the formula did. You just thought, hey, 2 standard deviation, 1 standard deviation. He wants between it, so it's going to be like 1.5 standard deviation. You don't get it. You don't get it. Okay. I'll use another example. Another example. Now, the people who got it, you can still answer, but the reason I'm giving a different example is because it makes more sense. Let's say I'm running a marathon. All right. So the average, for anyone who runs a marathon is, let's say, 20 miles. All right, 20 miles. And let's say the standard deviation is 5 miles. Now let's say I run 30 miles. If I ran 30 miles, how far am I away from the mean? If I run 30 miles, I am 2 standard deviations, right? What if I ran 25 miles? Is that 1 standard deviation? Okay. Now get ready. What if I run exactly 27.5 miles? How many standard deviations is that? 27.5 here, 27.5, 1.5, 1.5. Now, how did you guys come up with 1.5? I'll show you what you did. You don't know that you did this. All you thought of was, hey, what's the number between 2 and 1? It's 1.5. But here's actually what your mind did. You don't know that your mind did this, but here's what it did. It did 27.5, all right, minus the mean, 20, and that is going to be 7.5. And then you said, I'll divide that by the number of standard deviations, which is 5. And notice that'll be perfectly 1.5. Did you get it? We're seeing how far we are from the mean, subtracting it, and then dividing by the standard deviation. And what do you know? That's the formula. If he gives you any point, you just do that point, x bar, the sample mean, whatever point you're interested in, minus mu, the actual mean in the middle, divided by sigma. And that's exactly what you're doing. That's exactly what we did. We did 27.5, the point we're interested in, minus mu, which is the sample, the population mean, sorry, which was 20, the average was 20 miles, divided by sigma, which was 5. And if you simplify, it'll be 7.5 over 5, which will be 1.5. You see how you don't need to know the actual, you need to memorize the formula? You solved it without even knowing. All you're doing is you're saying, here, I'll make the numbers twisted, and you guys will still solve it. You guys will still be able to solve it. Now use the formula. Let's say I have population. This is 347. That's the mean. And the sigma is 22. What's the chance? Or first off, just give me the z. Just give me the z. Forget the chance. Just give me the z for the point 385. Give me the z value for this. So what you're going to say is you're going to say, hey, this is 385 away from here. So let's first find this difference. Let's first find all of this. It's going to be 385 minus 347. So let me find this one. This is it. 385 minus 347, 38. And then I'm going to divide this by the standard deviation, which is 22. Right? So 38 divided by 22 equals 1.72. So guess what? If 1.72, chat's in the way. Okay, 1.72. So if I asked you, what's the probability of getting someone who's on 388 or beyond it, then what you would do is you would go back to the Z table and you would search 1.72, 1.72. All right, so here's 1.7. This is 1.70, 1.71, 1.72. So 0.043. So a Z value of 1.72 would give me a p-value, a probability of 0.043, which translates to 4.3%. How do you know the probability of Z table? You can't. You have to use Z table, right? Z table is your reference. That's the only way you convert the Z to the P, or the P to the Z, alternatively. So yeah, so you would tell me the probability of getting someone who's 388 is 4.3. Now, did you have to memorize the formula? No, it makes sense. You minus this part from the mean, then you divide by it. But I can solve all this with you can solve all of this till you reach the Z, but then you gotta stop. You got the only way you can switch Z with the Z table. If sometimes you can make it the opposite. Maybe he tells you this is 20%. So find me this number. So now you have to work, basically, if such a question were to occur, you go here and you try and find 20% here in this part of the region. So let's try and find it. Let me move the camera a little. So here it is, 20, 0.20. So then you would go and you would see, oh, it's a Z value of 0.84. So now you got the P value. 20% basically means your Z value is going to be 0.84. We're going to do a lot of examples. Yeah, so there's a 4.3% chance of getting 388 or more than that. There's a 4.3% of getting 385 or more than that. That's how you answer this question. So let's take some more examples. I'll show you some more examples. Just let me get the Z table. Sorry. Just let me get the Z table. I want it to be in every slide. Just put it there. And just, oops. All right, all right, now we have the Z table in a lot of slides. So that's good. And do that. Go to Zoom and share. Just 1 sec. I'll get to all your questions. I swear to God, I see all the questions. Just give me a second. So where do we get 4.3 from the Z table? Yeah. What's the name of the value we got from the Z table? It's called a p-value. All of these are called p-values. P stands for probability. P-value, by its definition, means the probability of getting a certain point in the distribution or more extreme than that point. In other words, i.e., more beyond than that from that point. So that's the definition of p-value. Is this the last concept in the lecture? It's the last concept in the entire crash course. The next lecture, it just gives you a few more concepts and then repeats this whole Z table business. So we're just almost done. You know, I know it's like, oh, Khaled, you spent like 2.5 hours on the first lecture. No. We finished this. We're done. We're actually completely done. We just have a few more theoretical concepts that might take us half an hour to finish. So don't worry. You just search the body for 20% and find the Z for it. Yeah. Oh, like 0.2. Yeah. So 0.2. So we'll do more examples. So let's do another example. I'll give you loads of examples. I made like 5 million Z tables. We're gonna keep doing every single example. So you all will solve with me. Okay. So I'm gonna give you this example. Let's keep it simple for now. Okay. Let's keep it simple. Can you explain why we find the Z? Like I'm a 5-year-old, please. I will. We're gonna do a lot of examples. Okay. So all of you, like get a paper and pencil out. Like draw this with me. Think about it with me. So here we're gonna start, okay? Let's say the mean for this distribution is 50. I'm not gonna make the numbers easy for you guys, just because I want you to actually focus on using the z table. So let's say the sigma was 22. Right. I'm interested in let's say 84, right? Or no, not 84, 81. Let's say 81. So I want you to find me what's the probability of getting 81 or more. All right. So your job right now is to find a z. I want to see an answer which is a z value. Now I'm going to calculate it alone. I'm not going to show you what the answer is. Then we'll calculate it together, because I want to see you guys if you can solve it together. Even the people who don't understand it, it's fine. Put the wrong answer and we'll discuss it over and over again. So I'm going to do this alone. All right. I just want the z for now. I just want the z. All right. So if all of you did 81 minus 50 over 22, you're all right. You'll do equal. You'll get 1.409. I saw some people say 1.49. Careful. Don't make that mistake in the exam. 1.409. Right. So now this is our z table. This is our z. I just want to round it up because I don't like this. So 1.41. Can we all agree on 1.41? Does everyone understand why we got this z? I want to see the chat box literally with all the s's. If one person doesn't understand, it's fine. Okay. All right. Good. So now we all know why we got this z. Now I asked you for a probability, not a z. So I need to move this camera, and we need to. Oh, I can put it down here. That's awesome. Okay. I really chose the worst place to do this. Okay, so forget it. So 1.41, right? 1.41. So where's 1.4? We have 0, blah, 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 and then 1, and then there we go. 1.4. Right? This is 1.4. So now we don't want 1.40. We want 1.4. This is 1.40. This is 1.41. So the chance would be 0.079, which would translate to 9, which would translate to 7.9%. So the answer would be there is a 7.9% chance of landing on this value, which is 81, or beyond that value. How about if we have less than 50? All right, yeah. So we're gonna go over. We're gonna go over it. We're gonna go over it. Don't no need to confuse anything. We're gonna go over it. Just let me find the solution for this. We're gonna leave that there, and we're gonna put the chat on the left side. Is it important to round up? Yeah, I mean, it's not important, but like you're gonna land here. You're gonna land here. You're gonna get this answer, and the answer, if you round up, is gonna be actually this answer. So I think it's important to round up, right? You're gonna be stuck between either 8.1% or 7.9%. So in the exam, I think it's better to round up because 1.409 is not 1.40. It's very close to becoming 1.41. It's like, for example, would you say that? Yeah, it's round. Like you understand. It's round. So now, since we all understand level 1, let's bring it up a notch. Let's take it more complex. Let's make it more complex. So we have, let's say. So I want everyone to do this with me. Let's say the mean is 80, and sigma is 7, all right? And I want, no, use the rounding rule. If it was 1.401, it's 1.40. If it's 5, if it's 1.05, then you round up, right? Anything else, you don't round up, right? So just round like you used to round in high school. So let's say, so 92, okay? I'm trying to make the numbers not fit. I want them to be tough for you guys. So now I want to know what's the chance of getting 92 or beyond that. Oh, sorry, not 92. Oh my God, 92 is over here. Sorry. Um, not 92. Yeah. No, 72 will be too easy. 70, 70, 70. Let's say 70, right? Because it's not going to work with the standard deviation. So 70. So I want to know what's the chance of getting 70 or less than that. You can probably tell I need another cup of coffee today. So yeah, what's the chance of getting 70 or below 70? So I'm going to do it now. I want you all to do it, then we'll do it together. All right, so let's do it together. Yeah, you guys are all right. So basically, all you do is 80 minus 70 divided by 7. So it's 10 over 7. That's going to be 1.42885. So 1.4. Let's just put it 1.43. 1.43. Because I want to round up because this is 8. It turns it into 3, right? So this is our z value, correct? All right, so hold on. Some of you are saying it's negative. Now look, whoops. Now look, is this the, yeah. When we're on this side, since it's symmetric, since we're only working with normal distributions and it's symmetric, the z goes both ways. The z works both ways. So it doesn't matter if it's negative. A negative z just means that you're working on the opposite side. It's fine. Either you do, 70 minus 80 or 80 minus 70, doesn't matter. Doesn't matter, okay? Because at the end of the day, you know that you're on the left side. You know that it's negative or whatever you want to say. If you want to put it 70 minus 80 or 80 minus 70, doesn't matter. Doesn't matter. You're going to get the same z. It's just going to be negative. So negative just means you're going to the left. It doesn't matter. Absolutely doesn't matter. What's important is that always remember the p value you get is always going to be that point or beyond. That point or beyond. All right. Keep this. This is very important. Okay. So we got 1.43. What's it going to be? 1.4. This is 1.40, 1.41, 1.42, 1.43. So the chance is 7.6%. That's the chance of getting 70 or less than that. Get it? So are you all convinced with 7.6? Can I see some yeses just so I can know that everyone is understanding this? All right, good. Okay. So now we're still at level 1. Now let's take it up to level 2. All right, here's how he likes to make things complicated. What's the chance? Yeah, you multiply the value you get by 100 to get the percentage. Yep. So, or you can just do what I do. I usually do like this is 0.076. I just move the decimal places 2 points, so the decimal should be here. So 7.6%. It's the same as multiplying by 100. Multiplying by 100 moves the decimal place 2 spots. Okay. So here's where it becomes a bit more complicated. Let's say the mean is 85, and sigma is, I don't know, like 21. And let's say he wants to know what's the chance of getting 92 or less than that. So here's what you got to do. You got to find the z. The z will give you the p-value here. Then you do 1 minus that probability to get everything else. That's the idea, right? So let's do this together. I want all of you. I want to see only the z. Give me the z value. It should be. Right, so what's the z? What did everyone get? 0.33, right? 92 minus 85, and divide that by 21. It's 7 over 21. 7 divided by 21 is 0.33, right? So let's find 0.33. 0.3, this is 0.30, 0.31, 0.32, 0.33. So the chance is 37.1%. This is of getting this value or more than that. We don't want that. We want the opposite. So we'll do 1 minus. So what's 1 minus is going to be? 62.9, right? So that's how he tries to trick you. You'll think that, oh, p-value, yeah. So don't give him this. This will be an answer. This will be an answer choice. It's the wrong answer choice. This will be the correct answer choice. Can you repeat the last part, please? Yeah, sure. We'll do another one like this. Can we do this example on the left-hand side? Yeah, we'll do the example again. So let's do this again. We'll first do it on the right-hand side, then we'll do it again on the left-hand side. So we're going to repeat this. Listen, this is just a little tip is again, if you get a question like this in the exam, here's what you do. The first thing you do is you draw it, like literally draw it. Like do this, because he won't draw it for you. He might draw it for you, but like he probably won't. Draw this graph, the camera, draw this graph, and then put the mean where the mean is supposed to be. Put sigma up here like I do, and maybe it's like 6 or something. Do it like that, and then actually like map out what you want to do. So like actually map out whatever it is you want to do. Let's say the point he wants is, for example, this point that I put right here. So say, does he want everything after this point? Like actually mark it, like actually mark what your goal is. So now you understand where you want to go and where you want what you want to find. Always draw this mind map because it keeps you from making mistakes. So I'm drawing this mind map always here for you guys. The truth is he'll just give you mean and standard deviation as words, and then he'll give you the entire question as words, and then you have to draw to just not make a mistake. So let's do this again. Let's do 80 and sigma is 6. Right, sigma 6, and then the standard deviation, and the point I'm interested in is not 70, 90. So I'm interested in 90 or everything below 90. Now for the person who asked me to repeat this, when we used to do all these previous examples, the Z table always gives us the probability after the point. Now it's different. We want the probability before the point. So let's find first the probability after the point. And then since this is everything opposite to that, we'll just do 100 minus whatever this probability is. So our goal is to find the Z, then to find the p-value for this, then to do 100 minus this value. So did that make sense to the person who asked me to repeat it? So let's do this. Let's find the Z. What is the Z? It's going to be 90 minus 80. So did everyone get one? Yeah. So people got 1.66. So what's 1.66? Where is it? 1.6. And this is it. So this is 1.6. So 0.048. You all agree with me that to get 90, there is pretty much a 4.8% chance to get 90 or after that. But I want 90 and everything below that. Yeah, we should round up. So 1.67, 47. All right, you guys got me. All right, so 1.67 is going to give you 4.7%. But we don't want 4.7%. 4.7% is this area. We want all of this area behind 90, not 90 and after it, 90 and below it, 90 and below it. So it's going to be 100 minus 4.8. So 100 minus 4.7, sorry. It's going to be 95.3. So there's 95.3% chance, 0.3. So the chance to get 90 or less than that is pretty much 95.3%. Was that clear? The standard deviation was 6. Did it make sense to everyone? No. What part didn't make sense? Like, do you know how we got Z? The last part. Okay, the last part. Perfect. Remember how when we found this value, the percentage, the p-value, like here, I'll do this for you again. Let's say this is 80, and I want to find 90, and the standard deviation is 10. So what's, saying the last part got confusing. What do we do after we find p-value? Okay, I'll tell you guys. Just calm down. I made the numbers really easy here just because I want to explain it to you. When you get a Z value, here the Z is 1, right? Here the Z we can all agree is 1. 90 minus 80 is 10. Divide that by 10, you're going to get 1. And it makes sense it's 1 because if you go 10 points this way, you're going to get 90. Now, what's the chance of getting 90 or above 90? What's the chance of that? You go to here, and whatever p-value you find, that is your answer. That is straight away your answer, because this probability, whatever probability you get here, it's always going to give you the probability of finding the number you're interested in or after that number. But what if he tells you, I don't want that number and what's after that number. I want that number and what's below that number. So since the entire distribution is 100%, if I divide it into this part, and I told you this part is 4 or whatever, 16%, then what's this part going to be? I want Rima to answer. Where's Rima? Am I insane? Did the thing just close? Why is no one answering? If this is 16%, if this is 16%, and all of this is 100%, then what is this part? What is this entire part over here on the left? Yeah, Rima. Rima, 100 minus 16, exactly. So it should be 84. Does everyone understand why? So that's what you have to do. If he gives you a question like we did here, I told you I wanted 90 and everything below 90. Unfortunately, the Z table only gives you beyond this value. So you're going to get 90 and after 90. But we don't want that. We don't want 90 and after 90. We want 90 and below 90. So what do? The only way we can do this is we find 90. And after 90, then we do 100 minus that value. We'll get all the other part that we want. Did you get it? Can you go back to the slide that had the example of 47 or 4.7? Which one did you mean? You mean this one, 4.7? Yes, okay. I'm happy Rima got it. Okay. So 4.7. I think we should move to the next lecture. This is the next lecture. There's only like 15 minutes worth of theory, and then it's all of this again. We are in the second lecture. Yes, we are in the second. You're gonna be surprised. I'm gonna show you the second lecture. There's only like a few more concepts you need to know, and we're gonna finish them in like 15. It's just like, oh, I know this 15 minutes, and we'll get to them. We'll get to them. So this is multinomial. Yeah, this is multinomial distribution. So does this make sense? Is everyone clear with this? You don't have to say yes. If there's just one person that doesn't understand, just say no. I'm just going to see the questions. So if it's a probability of the value being between two values, we subtract the Z value from 1 and divide by 2. Wait. Iman, you are like 5 steps ahead. I will give you a very difficult question of what you're talking about, and we'll all solve it together, and I'll show you. Can you do an example from the left side? Yeah, we'll do an example from the left side. So if he gives you a number that's above the mean and wants the probability of that number and anything below, then you at the end you find the p-value, and then whatever p-value you find, you subtract it by 1 because you want to find the opposite of that. The opposite of the other.
Doctor,
Yes, Khaled.
this is okay. Sorry, this is Rima.
Okay.
I think my point of confusion after finding the Z value is deciding whether the Z value, should I round it up ولا لا? So if it's 1.666, for example, should I take the Z value as 1.7 or just 1.6 and then the P value as 0.07? So the latter,
No.
right?
Look, the p-value, you can't round it because the p-value, immediately what you get is what you get. Let's say the Z is 1.666. All right? Now we have a problem. We have 1.60, 1.61, 1.62, 1.63, 1.64, 1.65, 1.66, and 1.67. Well, which one do I take? Now, just round it. Since it's 1.666, this 6 will change this 6 to 1.67. So then you'll pick this one. So your p-value will be 0.047. Did you get it?
Yes, thank you.
You're welcome. Okay, so now we're going to do more examples. Did everyone understand this 1 minus the p-value thing? If you didn't understand, just say no. Yes, makes sense. Yes, definitely, bro. Definitely, yes. Just one doubt. If the question asks us to find the probability of a point on the left and beyond, yeah, probability of getting 70 and less, for example, round the second digit after the decimal. Yep. So yeah. Okay. So now we're gonna do the same thing, but on the opposite side. So let's do it. So we're gonna do it really quickly. Okay. So 80 and sigma is 7. Okay, and we want 70 or more. So we want all of this. So here's the plan. We're going to find the p-value here, finding the Z here, then we're going to do 100 minus everything, because the p-value will give us everything that's here, but we don't want everything that's here. We want everything opposite to that. So let's do it. So does everyone just focus? Let's give let's write the z's first. I can make sure everyone's right. Why is no one answering? Oh, there we go. Okay, 1.428, right? So 80 minus 20, you'll get like how do you round this up? Do we round this up or do we round this down? Yeah, so there you go. So, Sayeda, you got it perfect. 1.43. This will change this. So now let's search for 1.43. 1.40123. So this is 3, so 0.076. It will be 7.6%. Now, is this your answer? Is this your answer? Yes or no? Just say, is this your answer? Yes or no? No, this is not your answer, because this tells you 70 or less. We don't want that. We want 70 and more. So what do? We do 100 minus this. Yeah, so it'll be 100 minus 7.6 equal 92.4. That now, is this your answer? Hell yes, it is. This is your answer, 92.4%. All right. Now, to close this out, I'm going to give you the most complicated one you could solve yet. All right. If you can all understand this and solve this, we're gonna major W's, major W's. All right. That's what I mean. All right. So here's the question. You guys gonna be all right. All right. So here's the question. You guys focus. 80. Let's say a mean of 80, and sigma is 4. All right. Now I want the percentage between 86 and 77. I want to find the chance of finding this. So this is the most complicated version of it. So you know what you have to do? First off, let's agree on the plan. Our plan is to first find the z on this side to find the p for this side. Then what we're going to do is we're going to find the z for this side and the p for this side. We're going to add them together. Then we're going to find what this equals and what this equals together. Then we'll do 100 minus that total of those two, p values, and that'll be our answer. Do we all agree on that plan? Does everyone understand that plan? You don't, no. Look, people are saying 100 minus z from each side. No. Do not do this. Don't do this. Instead, add them together, because you can't do minus 100 and then minus 100. Add the two p values together, then minus 100. If you do minus 100 minus 100, you're actually making a mistake. You're minusing 100 twice. That's wrong. So yeah. So let's solve this on a different slide. I forgot what I said. Oh, let's not solve it. Let's just do this straight away. So let's solve this side. Can I erase this? All right. So you guys can start solving it. Let's start solving. I'm going to start with the z value on the right. So let's do the z on the right. So it's going to be what? 86 6 over 4, right? So 1.5. So the z is 1.5. So this side, does everyone know why z here is 1.5? 0.67. So this side is 6.7%. This side, okay? Guys, relax. Why are you guys all answering so quickly? Swear to God, it's like a race. Like, just take your time with it. Take your time with it. It's fine. It's not gonna like run away. Let's do this side now. Right? Does everyone know why this side is 6.7%? Yes, okay. So let's do this side now. So 77 minus 83, 3 over 4 is 0.75. What is 0.75? 0.012345. So it's 22.7%. 22.7%. So look, this side is 22.7%, and this side is 6.7%. So to find all the things in the middle, what we can do is we can add these two together. 6.7 plus 22.7 which is 29.4. And then 29.4 is just this and this, but we want the side in the middle. So we do 100 minus this. And we'll finally get 70.6. Can you do 93 minus? Yeah, I mean, you can, but like, no, please don't confuse. Hamza, you are really just trying to confuse everyone. You can do it, yeah. You can minus this first from 100, and then whatever result you get, you just minus it from here. You can do that. Just point is, don't try and confuse yourself. Just add them together and then just minus them. You can do it however you want. Just don't do 100 minus and 100 minus. It's wrong. Yeah, okay. How are they going to phrase this question? Yeah, they'll tell you in a specific, they'll literally just write to you. What do we do after getting both p-values? You add them together and minus 100 because you don't want the outside parts of the p-values. You want everything in the middle. So if that side is 6%, that side is 22%, but you want the sides in the middle, if everything is 100%, then 100 minus the addition of those two will equal your answer. And that's exactly what we got here. So how are they going to phrase this question? They're going to tell you in a specific population of hypertensive people, blah, 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 the mean is 80, sigma is 4, whatever, and we're interested in seeing what is the probability of getting a random person between 70 millimeter mercury systolic of 77 and between 8 to 86. What's the chance of getting someone randomly who has a systolic pressure like that? It's obviously like really low because everyone has like on 120 and everything, but you get the picture, right? You get the picture. Like let's say serum cholesterol level. That's the example in this slide. What's the chance of getting a serum cholesterol level of 77 to 86 in this population? Right, so that's how they'll phrase it. So always, please, I am begging you, don't try and do it mentally. Just, just draw it. You like literally do the thing and then this and then say, okay, so the mean is 80, the sigma is like 4, and then he wants this area and this area, but he wants the stuff in between. Then you have a goal to work towards. Then say, okay, I'm gonna find this first, I'm gonna find this first, I'm gonna add them together and then get 100. Just work like that, because if you don't work like that, if you work mentally and everything, you're gonna make a mistake. Simple as that. 22.7 is for everything after 77, right? Yeah, not after. Look, this is what I'm saying, not after, beyond. So it's for 77 and less than 77, right? This side is for 86 and more than 86. Does it make sense? So does everyone understand this? Does everyone understand this? Yes. Congratulations, we actually finished the 2 lectures. Now we're just gonna go over a few more, like theoretical things, and we're gonna talk about 5% because it's a really nice story, and I love telling the story every batch. So yeah, major W in chat. I sound like a streamer. All right, so I'm gonna stop sharing this, and what's the final answer? I showed it. It's like what was the final answer? It was 70.6. 70.6. All right, so let's keep all the annotations. Geez, dude, if you see all the things that I drew, it's like a crazy person writing. All right, so let's share screen and let's go back to the lecture. All right, so let's go to the first slide, normal distribution. And I'll do this, go to Zoom, and then share. And despite me always talking about how Zoom is just bad to use, it's actually really nice once you start to get used to it. Yeah, 29.4 are the extreme ones, yep. So now let's go over the slides. Let me show you how simple it is. We're gonna fly through the slides right now. Yeah, normal distribution, bell shape. Yeah, no, we know it has one mode, symmetric about its mean. Its mean is represented by mu, which is a Greek letter because they love Greek letters for populations and Roman letters for sample. But yeah, but now we're starting to use letters, which is nicer. Standard deviation is represented by sigma, the amount of dispersion around the mean, which is pretty much mu. The both mu and this are completely defined in normal curve, which are, I told this to you in your 3rd lecture, that you really only need the mean and standard deviation to be able to know the characteristics of a curve. This is what the normal distribution looks like. The shape really just looks like, it's a beautiful symmetric, bell-shaped curve. One thing he might tell you is that you see this 1 standard deviation. At this point, it is exactly where the curve becomes concave to convex. It might not look very clear when it's like a straight line, but you need to know that. That's a theory thing. It might be like which of the following statements is true. And at 2 standard deviations, it turns from concave to convex. That's wrong. At 1 standard deviation, it turns from concave to convex. All right. So that might be That might be a theoretical question. You need to be able to, pick it up and just answer it. So let me just get rid of the chat. Are mu and this parameters or statistics? I want you guys to answer this. Right? So what are they, parameters or statistics? Parameters, right? Because we said population parameter. They're using Greek letters, so it's this. What happens at one standard deviation? Look, the problem is the curve doesn't actually show it that well. Look, let me draw a curve for you. It goes from concave to convex at the one standard deviation. That is like theory that every person needs to know about the normal distribution. For any normal distribution, at the one standard deviation, the curve goes from concave to convex, right? It switches shape. What's the name of this lecture? It's called probability distributions. All right, so standard deviations. I saw this point in slide 44. Yeah, they'll talk about it. So yeah, well, you all know why it's mu and sigma are population parameters because we use Greek letters for the population. Many biological random variables, they are approximately normally distributed, which is why it's important to be able to study a normal and multinormal distribution. An example, for example, serum cholesterol, mu this, sigma that, blah, blah, blah. What's the chance of getting more than 245? Blah, 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 blah. We did all of this. And the chance Z, you find Z, we talked about all of this, yeah. And here's the point that was mentioned. Standard deviation. This is an important theory point, right? Again, right now we finished calculation. I'm talking about theory now. So it could be a question that's like, which of the following statements is correct? And you need to be able to understand that it's not going to be about calculation. It's going to be about a theoretical concept, a theoretical point. This is one of those theoretical points. At one standard deviation, it turns from concave to convex. Yeah, so this is just all the same table areas. It goes for beyond that area. And these values are really important. I want you to memorize these values, okay? So if the Z, can anyone tell me, like, does the Z being 0, it being 50%, does that make sense to you? It should make sense to you because with a perfect standard deviation, if the Z is 0 standard deviations, that means it's going to cover all of this area. So it's going to cover 1/2 of the distribution, exactly. So 0 is half. The reason they like 1.64 and 1.96 is because these numbers are very important when it comes to research. So researchers typically, they memorize these Z values, but now no one uses the Z table anymore. They use T tables and stuff. So we're going to ignore these numbers. But especially for STEP, they like asking about 0.5 and 0.25. And we'll talk more about why in the next lecture. Why 0.5 is such a special number. And we'll talk about it later. But memorize these numbers: 0, 50, 1.64, half, or not half, 5%, 1.96, 0.25, right? Half of 0.5, or 0.05 rather. This is the formula. You don't need to memorize it anymore because guess what? You already know it. It's already in your head. Can you please repeat why 0 is, yeah. So what does Z mean? Z is the number of standard deviations. If we have this distribution and Z is 0, that means we're starting from here. It means if this is 80, I'm telling you, what's the chance of getting 80 or anything beyond 80? So what's that chance? It's definitely going to be 50% because it's half and half. It's if we're starting from the mean, it's half and half. Did that make sense to you, Huda? I need an answer. Yep. Okay. Perfect. So now you don't need another formula. It makes sense. Z represents the distance between x, yada yada, in terms of standard deviations. In other words, Z is just the number of standard deviations. Since the standard normal distribution, blah blah blah. This is all stuff that we talked about. The area under the curve to the right of Z is equal to the area of the curve left to Z because they're equal. That's why I told you that it doesn't matter if you get a negative Z or a positive Z because either way it's going to be similar it's going to be exact in a symmetric distribution. Again, if you got like 1 and -1, it's still going to be 1 and you're still going to get this value. So it just doesn't matter. So here he's showing you, he's proving to you why in the third lecture they told you that the empirical rule says that there is 67%, if you check this area. If you try and find this area in between, what you can do is find the standard deviation, find the p-value here and the p-value here, and then add them together and then minus them from 1. And you'll get this value. So he's proving to you the empirical rule in lecture number 3. We talked about this. We talked about all of this. If normally distributed, then Z because table. if you try and apply a non-normal distribution and try and use the z table, the z is not gonna help you much. Like for example, it'll be here, and if you get a really wonky distribution, it won't be the same z. You won't get the same p-value. You won't get the same everything. Like you might get the same z, but that z does not really mean much because this is not a normal distribution. So it's you have to be careful when you're doing that. In practice, we often assume variables are approximately normal and then use z. So this is important. Every single distribution you get, it's usually not normal. So in the second lecture, the small little theory is how can we make non-normal distributions normal? How can we make that assumption? How can we best make them? So we'll talk about that. He gives you another example. We already did a lot of examples. Another example, another example. You can do the examples by yourself and then just check the answer and see what you did wrong exactly. And you can also message me on Twitter so you can actually see if you have any more questions. Okay, so he gives you more examples, 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 more examples. We're done. See? And guess what? I'm gonna show you lecture 2 right now, and you're gonna see it's just a few points about like how to turn a non-normal distribution to a normal distribution, and then it's gonna be full on the same thing. Examples on top of examples, on top of examples, on top of examples. And yeah, so we pretty much are very close to finishing. Let's let me open the lecture. Do you guys want to take a break before we do this lecture? Enable editing, animation, slideshow. All right, I'm not seeing chat. Just 1 second. All right, now I'm seeing chat. Can you see the? Yeah, you can see the screen. Okay. All right, let me just read. A lot of you are talking. A lot of you. Okay, can you guys stop talking? I need to see. I legit found this lecture so hard. I'm happy to help. We keep going. The lecture we just did. Yeah, I'm happy. Yeah. It's usually it seems very hard, but once you see many examples, once you see all the different tricks that can happen, it sort of becomes easy. 5 minutes would be great. Look, honestly, I want to break. So just 5 minutes, Yeah, just 5 minutes. I'm not gonna. I'll be here. I'm not like. I just want to rest my voice a bit. So yeah. Remember this stuff. Probably can't see what I'm moving, but I'm just moving the camera in the chats. All right. Okay, so what's the idea of the sampling distribution of the mean? Basically, it's one of the most important things in statistics. One person found it out, and it essentially boils down to I can turn any distribution. If it was like this, or like even like a block, if it was like a block, I can turn them somewhat into a shape like this. Somewhat, like it looks very close to a normal distribution. Even if it was like positively skewed, if it was negatively skewed, I don't know, like you get the picture. I can still do this technique and I can make them somewhat normal, or at least more normal than what they begin with. Everyone's here, right? I'm worried I'm just talking and no one's here. Okay, good. So there's people here. All right, so what's the idea? I'm just gonna skip ahead over this. We'll go back to it. The idea is that, you know what? Let's just stop this. I'll go to the white screen and I'll show you exactly what they mean. Okay. Let me go back to Zoom. Share. Put that. Share. All right. So this is exactly what they mean. You get like, yeah, there you go. Okay. So sometimes you'll have non-normal distributions. Like let's say it was skewed heavily like this. We can actually get it to look somewhat like this, somewhat like this. It doesn't become exactly like this, but somewhat it could look somewhat like this. The idea is very simple. This population you grab a certain amount of people, you take their mean and you plot it. You take their mean and you plot it. You take another 3 people, you put their mean. You take another 3 people, put their mean. So if we have this population, if I take 3 people, their mean was, for example, 10, I plot it. And another 3 people, their mean was 11, I plot it. Another people, and I keep doing that like 1,000 times. Basically, the mean is more likely, the mean of 3 people is more likely to land in the middle than, for example, the raw value by itself. And if you don't believe me, I'll prove it to you. So here's it sounds insane the way I'm going to show it, but it's actually happens. I'll show you how it happens. So look, let's say we roll a die. Okay, back to the die and everything. So 1, 2, 3, 4, 5, 6, right? Now, the chance is either 1 out of 6, or if we go higher, it's 2 out of 6, or if we go higher, it's 3 out of 6, yada, yada, yada. The chance, if we roll it once and we get 1, like what's the chance of getting 1, assuming we roll it once? What's the chance? Yeah, so it's 1 out of 6, right? So we put this point right here. The chance to get 1 is 1 out of 6, which is this point right here. What's the chance to get 2? It's also 1 out of 6. What's the chance to get 3? It's also 1 out of 6. So notice, this is not even close to a normal distribution. It is just a straight line. It is what we call a block, literally a block, right? It's a block of data, not even close to even being a distribution. Look at how when we take means, it actually turns into a normal distribution. So let's say I'm going to roll the dice 3 times and take the mean of their result. So if I got, for example, 1, 1, and 1, I add them all together, then divide them by 3, and I get the answer. So if I got, for example, 6, 6, and 6, I'll add them, then divide them by 3, and so on. So let's say, for example, what's the chance that I get, if I throw through the dice 3 times, what's the chance of getting a mean of 1? What's the chance of getting a mean of 2? What's the chance of getting a mean of 3? A mean of 4? A mean of 5? A mean of 6? So hold on. Here's what actually happens. How many different ways can you get a mean of 1 when you throw the dice 3 times? There's only one way. You get 1, 1, and 1. So 1, there's only one way. It'll be the lowest way, right? The lowest amount. I forget what the probability will be. There's only one way, and it's out of, for example, let's say it's out of 70, right? So 1 out of 70, right? I don't know what the whole sample space is, but let's say there are 70 different combinations, whatever, blah, blah, blah. Point is, there's only one way to get a mean of 1. You get 1, 1, 1. That's the only way. What's the way of getting a mean of 2? Well, there are numerous ways. You can get 2, 2, 2. You can get 1, 2, 3, and you can get 3, 2, 1. So basically, I found 3 different ways to get a mean of 2. So getting 2 is more likely than getting 1. What about 3? Well, now it's even more likely. I can count them all for you. 3, 3, 3. 2, 3, 4. 4, 3, 2. 1, 3, 5. 5, 3, 1. So look, I have even more ways. Now when you get to 4, we start to go the opposite of 3, so it's going to be the same, and then 5 will be the same as 2, and then 6 will be the same as 1, similar to how Pascal's triangle was. So notice how this little block, this block of data, turned into an actual normal distribution. That's the idea of the whole concept of sampling distribution of the mean. Basically, if you have any distribution, if you do this technique where you take 3 people from here, 3 people from here, and then you find their mean and then plot it, or then 3 people here, find the mean and then plot it, 3 people here, find the mean and plot it, 3 people here, find the mean and plot it, 3 people here, find the mean and plot it. Basically, it's going to be more normal than this idea. I see some people referring to the lecture 4 in combination. Forget all that. The only thing I'm telling you is that if you work with the raw values, on average, you're going to get really not normal distributions. When you take those raw points and try and take, for example, any random 3 points, finding their mean, then any another random 3 points, then finding their mean, and another random 3 points, then finding their mean, that distribution that you just made, which is called the sampling distribution of the mean, it will be more normal. That's all you need to know. You don't need to know how to calculate it, how to do all this, all that. I'm just proving to you that look at how even we have a block of data, and somehow we turn it into a normal distribution. Get it? So when So getting an average makes, yeah. So getting an average makes it more narrower. It makes it more normal. The whole idea is that if you have a distribution of people, by doing this technique where you take 3 people from here, find their mean, and then plot it. 3 people from here, find their mean, and then plot it. 3 people from here, and then find their mean and plot it. 3 people here, and then find their mean, which is here, and then plot it. 3 people here, and then find their mean and plot it. 3 people here, and then find their mean and plot it. At the end of the day, if you do that like 1,000 times, all the means will be really close together in the middle. Very rarely will it be on the side. Therefore, you will get a probably random, it'll be a normal and more narrower distribution. It'll be a more normal and a lot more narrower. All right. So, yeah. Can you repeat the last point? Look, it is just one point. The entire point is when you have a distribution, any distribution, it's not normal, it's bimodal, it's whatever. It's like this. You can turn it into this just by doing this technique of taking multiple people. So, are we talking about increasing sample size? No, we're not talking about increasing sample size or that. All I'm saying, if we have, like, this is literally all I'm saying. I don't know where you guys are taking all this information from, but this is all I'm saying. If we have this distribution and we want to make this more normal and more narrower, all we need to do is just take any 3 points in here, find their mean, plot it. Take any 3 points. Yeah, I gave you the example of the die. Yeah, so we took random points. These are all, for example, let's say that, okay, another example. Okay, sorry. No. Okay, so let's say this is the height of people, right? So every single point is a person. I'm really sorry, my cat's going nuts. She does this sometimes. Point is, this is the height, for example, 160 centimeters, 180 centimeters, and then 140 centimeters, right? And then this is like the number, or no, this is the number of people, and this is like 160 centimeters. This is 180 centimeters. This is 140 centimeters, right? So the entire idea is that if we have a distribution, and this is filled every single point in here, every single point, like there are a lot of points here in the center, and less points as we go to the side, but there are a lot of points here, right? If I take any 3 random points, or 4 random points, or 5, let's work with 5. If I take 5 random points here, here, if I find their mean, and I make a new distribution, and I plot it, and I do that again like 1,000 times, I take 5 random points, I plot their mean, for example here, I take 5 points, plot their mean, for example, I got here, 5 points, their mean, got here, 5 points, their mean, got here. Eventually, if I do that 1,000 times, the sampling distribution of the means will end up looking narrower and more normal. That's the entire idea. That's all you need to know. That's all you need to know. Literally, not more, no less. The reason is because when you work, like, the reason is simple. It's because when you try and work with means, sometimes, more often than not, you might get a point on this side that's very extreme and a point on this time that's very extreme. So when you take their mean, they actually connect and they go in the middle. Wouldn't that make our values a bit more inaccurate? No, it's the exact opposite. Your values become a lot easier to work with. They become more precise, and you're less likely to have outrageous values or the distribution of things that you can work with. Yeah, so this, if you find the mean of this distribution, this mean will be technically the mean of means. Now this distribution is called, just a regular distribution, doesn't have a name, but this distribution, its name is called the sampling distribution of the means. That's all you need to know. The sampling distribution of means will become more normal and narrower. That's all you need to know. So let's say we have 100 people, we take 5 random time. Are we limited to 20 random picks? Yeah, if you have like 100 people, yeah, if you take 5 every time. The thing is, like, you can do this. If you have 100 people, you can still pick any random 5 a million times. It's fine. It's not like you only have to pick one person once. No, it's fine. You can, like, let's say I picked Adam, John, and I don't know, Thomas, and then Adam, Tom, and John. There's like a show with Adam, Thomas. All right, point is, if I pick Adam, John, and Thomas, I swear to God, I heard those names. Point is, if I pick Adam, John, and Thomas, it doesn't mean that the next time I pick the 3 people, Adam can't be one of them. Adam can be one of them. Okay, so it doesn't matter. You can do this as many times as you want, but usually they don't, like, You don't need to know how many times they do it. All you need to understand, the only thing you need to understand is that when you do this technique, you're making things more normal and you're making things more narrower. And that's the beauty of making a sampling distribution of means. Sampling distribution means it's where we get 3 means to make the graph more normal. So the more times we do it, the closer to the mean we get. The more normal and the more narrower it gets, right? The more times you do it, the more normal and the narrower it gets. That's the idea. That's the only idea that I'm mentioning here. Yeah, that makes sense. Okay. So same thing of how I showed you here. Look at how we have literally a block of data, and by taking means, I threw the for example dice and so on and so forth. Eventually, if you actually do the sampling distribution of the means of this piece of data, you'll actually get this distribution. So look at that. We turned literally a block of data, a literal like rectangle, into a normal distribution. So yeah, that just gives you an idea of how strong using this technique is, and it revolutionized this sort of idea, because we always say, oh, we're going to assume our distribution is normal. Well, now you don't need to assume. Now you just make it very close to normal, and then, yeah, okay, assume it's normal. It's fine, because it's very close to normal, right? So that's the problem mainly with biostats, that we assume a lot of things. But now we don't need to really assume much. Yeah, so I'm going to show you now the slides. So for example, this is a distribution. If you apply the sampling distribution, you'll actually get an even narrower. So it will be something even narrower like this. You get it? So it'll be even narrower than the actual distribution, right? And you know, this is because they did the technique. Now, yeah, so yeah. So if you take a sample of 3 people, measure their systolic blood pressure, and then we calculate their mean and write it down, and then we do this 1,000 times. Basically, if we plotted a frequency of all the different means, we would get this. Look at how this is a lot wider. Now it's a lot narrower. And look, this was with 3 people making a mean. 3 people making a mean. If you pick more and more, for example, 5 people making a mean, 7 people making a mean, 20 people making a mean, it gets even narrower. So look, what if n was 20? For example, you take 20 and get their mean. You take 20 and take their mean. You take 20 and take their mean. It gets even narrower. So now they needed a way to highlight this. They needed a way to highlight this. How can we relate a decreasing variability with an increase in sample size? Well, in math, whenever you have an inverse relationship like this, what you do is you put one side in the numerator, right? So equal, right? And then there's a number here, and then number here. You put one value here and one value here. Therefore, they're inversely related. And that's exactly what they did. They just said, you know what? We'll go to it. We'll just say the standard deviation is pretty much sigma divided by square root n. Now, where did they come with square root? It's because, remember, variance, they initially did it with variance. They just put over n. Then they realized, oh, hey, but no. If we want to do standard deviation, you have to do square roots and square roots. So it's going to be s over radical n. You get it? So again, sometimes he will, this is important. If he did not mention, for example, we are doing this technique, didn't mention if there's a sampling distribution, didn't mention anything, do not use this formula. Use how we calculated sampling standard deviation in the 3rd lecture. Remember that? Where we calculated the variance first from the mean, and then there's n-1. Remember that? Yeah, that did not have over radical n. You only use this if he's telling you in the question we're using a sampling distribution of the mean. If he tells you that, remember that once you get the standard deviation, divided by radical n, divided by square root of n. Okay? Because the sample mean, this is the only way we can represent that a sampling distribution of the means can actually get narrower. In other words, the standard deviation is going to get less and less as the n keeps going higher and higher. So can you please repeat? Yeah. The entire point is that if he mentions to you that we're using a sampling distribution of the mean, you want to use this formula, right? If he tells you we have a sample of 9, you want to use this formula. If he tells you there's a sample and we're using sampling distribution of the mean, you want to use this formula. This formula where it says, I can't find my mouse. This formula where it says sigma over radical n. When it's just standard deviation of a population, or standard deviation, for example, he wants you to find sigma and yada, 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 and he gives you points, don't do radical n. Don't do radical n. You only use radical n when we're considering cases where there's a case where there's sampling distribution of the mean. That makes sense? Yeah. N is sample size for example, how many you picked. For example, here, in this example, they picked 3 people and got their mean. They picked 3 people and got their mean, 3 people got their mean, 3 people got their mean. So n is 3. If they picked 20 people got their mean, 20 people got their mean, 20 people got their mean, then the n is 20. So here, for example, if we do the first one, this would be radical 3. And for the second one, it would be radical 20, right? And that's the entire idea. Okay? So does that make sense? This entire principle, where points like to go to the center, that's called the central limit theorem, where by doing the sampling distribution of the mean, they not only get narrower, they get more normal. That's the entire concept, all right? That's everything you need to know, all right? Now, why is this relevant? Because we always say, oh, I want to assume that my distribution is normal so that we can find a p-value, yada, 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 a z, yada, blah, 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 blah. Well, now you actually know why we're doing this, because this process makes it more normal. And when we make it more normal, now we can actually say confidently that, hey, we trust that this is going to be a normal distribution, right? Now here he's giving you another example. Notice how this is very normal distribution. I don't think, this is diastolic blood pressure, and he's showing you that we can make them, for example, like here he tells you we have a random sample of 16 patients. So by the end of the day, basically, when you calculate z, remember how we said z is z equals x bar minus mu over sigma? Remember this? If he tells you there's a sample, well, guess what? There's a sampling distribution of the mean. So don't just put sigma over radical n. Another name for that is SEM. So just to make it very clear, if he ever says calculate standard deviation of a population, for example, you're going to do the thing we taught in lecture 3, right? There's no radical n, and that thing's called sigma. That thing's called standard deviation of the population. It's a Greek letter. It's that's why they use it for the population. If they're telling you, hey, we have a sample of 16 people, and we want you to find the z table and all that other stuff we did, the only difference that we're doing is that when we talk about z equal x bar minus mu over sigma, it's no longer sigma because he said sample. It's sigma over radical n, which is termed as SEM, standard error. Standard error. Sometimes they notate it as SE. You might find that in step 1 book. It says SE, and that's standard error. It's the same thing. Same thing. So is this clear to everyone? So if he tells you we have, sorry, can you repeat when we use this formula? If he says sample, use this formula with the SEM, with the radical n. If he tells you we have a population, yada yada yada, there's no mention of sample, there's no mention of how big your n is. When the previous lectures, no, the previous lectures were not about samples. The previous lecture, I would always tell you, for example, this is the average of the population, it's at 80, and sigma, remember here, I can prove to you that it wasn't about samples. I always said sigma, every single time I said sigma, every single time. Sigma can only be applied, it's a parameter, it can only be applied to populations. So everything we were doing in the previous lecture, it was all about populations. If he ever mentions sample and gives you the amount of people in the sample, please don't forget to just do the same thing that we just did. Z yada 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 x bar blah 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 minus mu x bar minus mu over sigma over radical n. Does it make sense? If there's any mention of a sample and how many people are in that sample, you want to use STM. You don't want to use sigma, because that right now we're not talking about a population, we're talking about a sample. Does that make sense? I need everyone to say yes. If someone didn't get it, just say no. So it's the exact same thing, but we're using SEM because of the sample. Yes, and I'm happy. We do this to get the probability of the sample. We do, look, yeah, we do this. Basically, he'll tell you this is the sample we got, blah blah blah, yada yada yada. He'll tell you, like, we'll do an example. We'll do his example, okay? So basically, here's what he's gonna tell you. He'll tell you that, you know, the population sigma is 10 and it's the mean is 105. Okay, so 105 and sigma is 10. Okay, so he's telling you in our random sample we got 110. He's telling you how lucky is that you know thing. Now what all of you are gonna do is, oh yeah, it's simple. So it's just, you know, it's like half, 0. Yeah, z is half, because, you know, 110 minus 105 over 10, that's going to be half. No. Don't forget, put that z, like, don't forget, he mentioned sample, so all you got to do is just z equals 110 minus 100. Isn't it 115? Yeah, their mean is 110. Their mean is 110. Like, he wants 110. Basically, he wants 110. All right, he wants the 110. Guys, oh my God, I have to really like explain this. The reason, look. I want everyone to calm down with the questions. Listen. Then the sigma of the population is 105. The mean of your sample is 110. Since there is any mention of a sample, just please keep this as a rule in your mind. If there's any mention of a sample, that means that we have to use SEM. Okay. Now he's telling you the population is at 105, and that his sample got 110. So how lucky was this choice? Basically, you do the exact same thing. You do the exact same thing. The only difference is that because this is a sample mean, not a population mean, you have to do z equals 110 minus 105, which is going to be 5, divided by, what was it? What's sigma? 10 over the radical n, which is 16, which is going to be basically 4. So it's going to be 5, right, over 10 over 4. What's 10 over 4? 2.5, right? 2.5. So z is actually 2. Did you all understand this? Yeah, the only reason we're doing it is because sample is mentioned. You do everything the same. Here, the only difference he's telling you is that, hey, this is a population with a mu of 105 and a sigma of 10. We have a sample of 16 people that got a mean of 110. What's the z value? The only difference is that you're just going to do radical n. The only difference. Previously, it just said, hey, we have a population of mu of 10 and a sigma of, for example, I don't know, like 6. And what's the chance of getting this value? No mention of sample, no mention of anything like that. So don't put radical n. Just solve it the way we solved it all the previous times, right? So here the z value is 2. Does everyone understand why it's z value is 2? All right, good. Now, since z value is 2, if we check the z table, the z value is going to be 0.028 or 0.0228, whatever. So it's going to be 2.28%, right? 2.28%. So looking up the z value of this, we get 2.3. Now, what does this probability mean? It means that, our sample, assuming it came from the population, again, this is, look, I'm gonna be honest with you guys. I'm gonna be honest, really. This concept that I'm sharing right now, it is the basis of testing hypothesis. It is the basis of the lecture you're gonna have after the midterm. All right. So if you didn't get it, honestly, if you guys want to stay here 2 hours and we explain it, I'd be happy to do that. But I'm telling you this right now. For now, just understand it like this, and just later on we'll diverge into it and talk about it after doing the final crash course. So what does this 2.3%? It means that in this population, our sample mean, there was a 2.3% chance of getting that mean or beyond that mean. All right. So since that mean was so little, we're going to assume that these are different populations. These two people come from different populations. Remember, you assume they came from the same population, right? The entire idea is that since it's a very low number, it's lower than 5%. The entire idea is that if you get a p-value lower than 5%, this sample probably did not come from this population. That's all that they're trying to share with you. All right. So do not ask more of that. Do not ask less than that. There is a whole lecture where we actually talk about this and actually try and discuss it. And it takes around 2 and possibly even 3 if you were like the 10th batch. And it takes a long time to actually talk about this, because it goes to this idea that can someone be 60 feet tall and all that garbage and stuff. So for now, the only thing I want you to know is that if the p-value, for whatever reason, if it was less than 5%, then it's such a small value. And this value, like, first off, let me tell you what this 2.3 means. This 2.3 means that there was a 2.3% chance that I got this sample mean, assuming they came from this population, the population that's in the question, this population with the 105 and whatever, sigma, whatever. So since it's a very small percent, less than 5, that's the agreed cutoff, we completely say that, hey, it's very lucky to get that sample mean. We're going to assume they don't come from the same population. If you didn't understand that, I honestly cannot be asked to do 2 hours just to explain this concept, because this concept is the basis of testing hypothesis. If you didn't understand it, just memorize it like that. I doubt he'll ask it to you, because this is the lecture after. This is not this lecture. All right. So the entire idea is that getting this mean or beyond that mean in the same population, in the same sample. No. Like getting this sample mean. Like the first assumption we make is that this sample, it came from this population, right? That's the first sample that's the first assumption we make. Then what we say is that if the p-value we got was less than 5%, it's basically so lucky that we get that number. We only had a 5% chance, or in this case, 2.3% chance to get that number. So probably they didn't come from that population. That's the entire point of it. Don't ask more, don't ask less. We're going to talk about this so much more in later detail with the testing hypothesis lecture. But that's the basis of it. That's the basis of it. This sample mean, the sample mean, we had a 2.3% chance of getting it. Since it was so lucky to get, we get rid of that assumption we made in the early. If it was something like 8%, let's say it was 8%, how would be asked about it? I doubt you'd be asked about it. Honestly, I don't know how you'd be asked about it, but I doubt you'd be asked about it, because this entire idea is the idea of lecture 2. The only thing here. This is how you'd be asked about it. Just memorize this for now, because honestly, spending 2 hours right now trying to tell you exactly what testing hypothesis is going to take too long. If your sample mean, after you compared it to the population, yada yada yada, and you got your p-value, let's say it was 7.3. This is how you interpret it. Since 7.3 is very likely, it's more than 5%, this sample mean probably really did come from this population. If, however, it was less than 5%, for example, 2.3%, like how we got it here, then we throw that assumption out the window. We say, it was very lucky to get this sample mean, so probably it didn't come from this population, right? And that's the basis of testing hypothesis. I really want, testing isn't included, but he has it here inside his slides. So that's why I mentioned it to you. So basically just know that 5% is the cutoff. If it's more than that, then the sample belongs to the population. If it's less than that, then the sample does not belong to the population. Just know that. Just know. You don't need to know more or less. All right? Isn't even included in the midterm, so I doubt. Yeah, he's not going to ask you on this. Just know the cutoff, 5%. Just know that that's the cutoff. If it's more than that, say it came from that population. If it's less than that, why 5%? We'll talk about why 5%. We'll talk about why 5%. So yeah, so he gives you more and more examples. You can keep doing them. Just remember that all of these examples are with SEM, right? All of these examples are with SEM. We made some assumptions. The assumptions were that, we knew mu and sigma. This is just preparing the next lecture where he's going to tell you, hey, we don't actually know mu and sigma. So how can we estimate mu and sigma? So basically, yeah, see you later lecture. See, so he's just preparing you to know this. So yeah. So except in the previous lecture, we considered, in the previous lecture, we considered population distribution. In this lecture, we're considering the sampling distribution, right? So for now, we will be given sigma though, right? If he tells you sample, use SEM. If he gives you just the population, no mention of a sample, no mention of how many were in the sample, no mention of anything like that, use sigma, all right? So now we'll be given sigma though, right? Yeah, you'll always be given sigma. You'll always be given sigma, right? But just remember, if you have a sample, use sigma over radical n. If it's just the population, no mention of a sample, just use sigma. And this is again the same thing, But here it was 108, not 110. So he got 103, he got 1.2. That means it's 8%. What is this 8% or 9% mean? It means, or what is it? 88.5. This is basically like, you'll see it here. He draws it. Yeah, this is all of this, opposite to this. So again, I feel like we solved so many of these that we don't really need to go over this. But yeah, he gives you another example. This is basically the opening to confidence interval. So this is again the same thing, same exact thing that we did at the end of the last lecture, which was this and this, find the p-value here, find the p-value here. But this time you might have SEM as opposed to sigma, and basically you can find this exactly right. So one thing, like this is about confidence intervals. So do you guys want me to explain confidence intervals? Because this entire slide is about confidence intervals. No, the capital no. Yeah, so basically he's just saying instead of doing the way, I'm not going to explain it, but basically instead of finding the p-value here and the p-value here, we can do this little thing that we call confidence intervals. But you don't have confidence intervals, so just forget it. Just forget it. What might be the use of these limits? Basically, you're going to have confidence intervals. If anything is outside of that limits, it's going to be included. Yeah, so it's not even included. So we're not going to talk about it. We're not going to talk about it. So here we go. We're finally finished this is the entire lecture. So it's just about SEM, the sampling distribution. It's about radical n, and it's showing you all the examples. But instead of just using sigma, we use radical n. Then he gives you a little thing about the, how sometimes we don't know sigmas here, like this. We don't know sigmas here. Trying to basically prep up the next lecture. Then he talks about confidence intervals, trying to again prep up the next lecture, and then finally he closes it out with y 5%. So I'll give you this example. This is the story actually. It's a real life story with I'm changing the math just to make it easier. So Ronald Fisher, which is one of the founding fathers of biostatisticians or biostats, he was actually he was not that nice of a person. He was actually a really rude person, but he was at this tea party, and there was this lady that said, "Hey, if you give me 6 cups of tea, all right, if you give me 6 cups of tea, and then you fill, for example, this one first with milk, and then put the tea, and then milk, and then tea, and then milk, and then tea, and then this one tea, and then milk, tea, and then milk, tea, and then milk, and I'm not gonna look. I'm gonna be able to know which ones you put the milk first and which ones you put the tea first. The tea first. Okay, so he sat there and he thought, this is probably, he's probably lying. But let me be sure. I'll do this experiment once with her. I'll calculate her chance of getting it right by pure luck. So what did he find that it was pure luck? I'll show you. It's actually, he did combination. So combination 6 and 3, it'll end up being 20. So do we have to really do this? 6 times 5 times 4 times 3 times 2. 720 over 3 factorial, 3 factorial. So it's going to be what? 6 and 6. So 720 divided by 36, 20. So he found out that there were actually 6 different combinations. 20 different combinations for these 6 cups. 20 different combinations. And only one of them was right. Only one is going to have the 3 milks first, and only the other 3 are going to have the 3 tea. So he said the chance of her getting it right completely by luck is 1 in 20. In other words, 5%. So if she gets it right, he'll say, she had a 5% chance to get it right by luck. So probably she didn't get it by luck. He set her apart from the regular population that gets it by luck. She's special. Just like how our sample is, if it's less than 5%, it's not part of the population, it's special. Here, let's say, for example, the chance was 10%. For example, it was 10, the chance was 1 in 10. He would tell her, 10%, you could still get lucky. Like, I'm not going to consider that lucky. I'll only consider it lucky if you get it right with a 5% chance. If you get it right with a 10% chance, 7% chance, 10% chance, they're like, no, this is luck. It's fine. I'll include it. Yeah, that's why 2% is by luck. So with the blood pressure example, what we were saying is to get that sample mean, we need a 2.3% chance of getting that. So that's very lucky, and we assume they came from that population. So obviously they don't come from that population, right? Because we're not going to get lucky by 2.3%. They're somewhat different. They're strange. They're special. And I found a mean that's very special. Did you get it? So that's why they made 5%. And it's a true story. The difference is there were 8 cups, and it was a bit more complicated. It was like one has sugar, one has this, one has that. Blah, blah. So luck validates the sample. Yeah. So luck, basically, if the chance of getting a sample was 2%, assuming it came from that population, it probably doesn't come from that population. It's probably, its population is somewhere like on the right, and that's why you got it. Because it's very lucky, it's very common for you to get that sample. Again, we're going into testing hypothesis. What I need you to know is just 5%. That's all I need to know. The tea lady, Just remember T lady. And there's this whole book about her, how she changed, statistics, how statistics revolutionized science. Yeah, if the sample was the chance to get the sample mean was 5% or less, then basically we consider that a special sample and it's not related to that population. The whole time you say, before you find out the p-value, you are always going to say, it comes from that population. It comes from that population. It comes from that population. Oh, we got a p-value of 2.3. It doesn't come from that population. It's special. If the p-value was 7%, you would say, oh, it still comes from that population. If it was 6%, still comes from that population. If it was 10%, it would still come from that population. If it was 2%, 3%, anything below 5% or 5%, you would say, hey, that's very lucky to get. So it definitely doesn't come from that sample, or that population, sorry. It doesn't come from that population. So with that, we actually finished. We finished. All right, so yeah. Does anyone have any questions? How did the number appear? It's not part of the population. No, see, Tariq, I'm telling you, everything before we find the p-value, we are saying, hey, we're going to get a sample, and this sample is part of this population. It's part of the population. We're always assuming it comes from this population until we get the p-value. The p-value is what decides. It tells us, are we right? Does it come from this population? Or is it 5% or less, and it doesn't come from that population? And this is the entire, basis around testing hypothesis. I kind of gave you a lot of things. So yeah, so we have more than just one population. We have more than one. Yeah, like for example, think of people who are, like for example, here's how it works. Let's say you grab a group of people, but they happen to be hypertensive. Now you don't know if they're hypertensive. All you did, you calculated their mean. Their mean was like 180 millimeters systolic. So you assume they come from the normal population. You're like, well, maybe they are normal, but I just got very lucky. Let me see how lucky I got. If their sample mean is for example 2% or like 180, and you calculate the p-value and it's 2%, you're gonna say, hold on. Now you're telling me that this sample mean that I got, that I'm assuming are just regular guys, I had a 2% chance of getting this? No, they're obviously not regular guys. They're probably just hypertensive guys, and I got very common if I consider them with their hypertension population, it's very common to get someone with 180. So I hope that sort of makes sense. And this is like, I really explained a lot of testing hypothesis, and this is just the, testing hypothesis. So yeah, can I get an A without studying this lecture? Man, like why don't, like, you have a lot of time. You can study this lecture. Yes, I have a question. I still don't get when to use same. Yeah, okay, so look. If it never says sample and never says the number within that sample, you don't need to use SEM. You don't need to use the radical n, sigma over radical n. If it told you, for example, sigma, if it told you, for example, we just have a population, like we've been doing in the previous examples, I've been telling you, for example, here, there is a population, and there is 80 here, sigma. Here, I'll show you all. I want you all to do this with me. Okay, we're not going to calculate. Just tell me, are you going to use standard deviation or SEM? Just write that in the chat. Okay, this is the distribution, this is the population, this is the 80, and this is sigma, which is 6. Okay, equals 6. I'm interested in point number 90 for whatever reason. Find me 90 and after 90. Are you going to use sigma or SEM? You're going to use sigma. You're going to use sigma. Right? Because I never mentioned a population or anything. I never mentioned a sample or anything. Now let's do the other one. You have a population with a mean of 90, and the sigma is 10, for example, and then you got a sample mean of 100, all right? And then the sample, it had 16 people. Are you going to use SEM or are you going to use sigma? Now we're going to use SEM, because I told you this is a sample mean. This isn't just a random point I'm interested in. This is a sample mean, and I told you exactly how many are in the sample, all right? All right, so with that, we finished. So before you all leave, we have 43 people here. I'm gonna, if they don't mention n then, yeah, so if they don't mention n, then you can solve it. So if they don't mention n, they're just telling you don't use SEM, right? If they don't, they told you don't use, if they told you don't use, if they didn't give you n, they're just telling you don't use SEM. Yeah, so that is sigma over square root of 16. So we do the sigma, yeah, exactly, you do the sigma method. So yeah, so since you're all here, I don't want any of you to leave. Just 1 second. All right, you're all welcome. Tell me thank you as much as you want. It's fine. But listen, all right. In the last batch, I was studying step 1 as I was giving them. Alhamdulillah, I finished step 1. I'm really satisfied, happy with the mark, extremely happy with what I did. And now I'm studying for step 2. And step 2 studying is a lot more, it's a lot weird. It's very, very weird. Right? It's things that are like very controversial and so on and so forth. So I told the previous batch to please give me dua for step 1, and I really feel like the dua they made and the effort that I put in, I feel like that cultivated to a mark that I really got satisfied with. So I'm asking of you guys the same thing. Okay, so just whenever you go into the exam and you really feel like the crash course helped you, please just remember, you can tell me thank you as much as you want. It doesn't matter to me. I don't mind if you saying thank you, but just when you're in your prayer, just remember me, because my exam is going to be soon. It's like in 2.5 months or something, and I'm finally done with everything. I can just not do another exam for the rest of my entire life until like after anything else. So yeah. So inshallah we'll meet again for the final crash course, inshallah, and yeah. Thank you so much. All right. So with that said, I'm gonna go enjoy the rest of my coffee and study, and yeah. So good luck to everyone, inshallah. I'll maybe put out a tweet to say good luck to everyone for your Biostats. I want to see everyone like that tweet at Khaled Eternal. Yeah, just casually just drop everything. And if you're interested, maybe you're gonna have dinner soon and you want to watch some videos, you can go ahead and watch some YouTube videos on youtube.com/Dr. Khaled, and just shamelessly putting everything. All right, so good luck, everyone. Can I share my screen to show you one of the previous lectures? I have a question. Sure thing. Go for it. Appreciate your time. You're all welcome. Just remember to please follow me on Twitter. And no, it's fine. I'm not following each other. But like, yeah.
Okay, I have a question.
Sure.
About when to use when we divide the radical n or not. So in this lecture, like, why didn't we divide by radical n if we are using x bar? So doesn't that mean that it's coming from a sample?
This is completely different. This is something else. This is just calculating. Like, remember when I just tell you sigma is 12?
Yeah.
This is how we find it. Like, can you go a few slides ahead until we find standard deviation?
Here?
Yeah. So I'm على طول giving you standard deviation. So all of this n-1 business, it already happened. It was the n-1 was every single data point in the entire population. Did you get it?
Yeah, okay.
Radical n is just of the sample. But whenever you find variance, you have to include, remember we talked about in lecture 3? You have to take every single point, find how far it is from the mean. So when I give you sigma, no one can ever actually find out what sigma is. But he's just giving it to you just so you can understand the theory. But it's impossible to know what sigma is, because how can you find like 100,000 points? So the n-1 is going to be 100,000 minus 1, and then you're going to get variance. You square root that, you're going to get sigma, technically sigma for that population. Then you do, if you have a sample and everything, then you do sigma over radical n. So this is just, I'm skipping so many steps about the variance and the n-1. I'm just giving you sigma straight away, right?
Yeah, okay, I got it. Thank you so much.
Perfect. You're welcome.